Hello, and welcome to the Sleepy Astronomer. Tonight, we're going to discover something unsettling about that faint smudge of light in the autumn sky. Something that changes not just how we see Andromeda, but how we understand time itself, and what it means when we say a collision is coming. Because here's the truth we've been dancing around, the revelation that takes a moment to settle into your bones. The collision isn't coming. It's already here. It's been here for millions of years. It's happening right now, tonight, as you settle in to listen. The great galactic collision between Andromeda and the Milky Way, the event we've been describing as future, as approaching, as billions of years away, has already begun. That sounds wrong, doesn't it? We just spent an entire journey watching these two titans approach each other across 2.5 million light-years of space, falling toward their inevitable merger 4 billion years from now. We traced their orbits, calculated their trajectories, witnessed their future collision in computer simulations. How can something that won't happen for 4 billion years have already begun? The answer lies in what collision actually means when you're dealing with objects this massive, moving this slowly, operating on timescales this vast. We think of collisions as moments, the instant when two cars meet, when a baseball hits a bat, when waves crash against rocks, quick, violent, definitive. But galaxies don't collide like that. Galaxies collide the way continents collide, the way weather systems merge, the way one season becomes another, gradually, invisibly, across spans of time so long that the word collision stops meaning what we think it means. If you're settling in for the first time, welcome to this journey through the unseen war. And if you've travelled with me before to explore Andromeda's true size and witness the coming galactic showdown, it's wonderful to have you back for the most unsettling part of this story. Tonight's journey asks you to reconsider what you thought you knew about the future, about distance, about safety. Because the collision we've been treating as distant and abstract turns out to be immediate and present, just operating on a timescale that makes it invisible to creatures who live for decades rather than eons. Wherever you are tonight, settling in for rest or simply curious about the slow violence unfolding in the darkness around us, I'm so glad you're here. If this journey through the hidden beginnings of galactic collision helps you unwind or fills you with that particular kind of cosmic perspective that comes from understanding just how patient the universe can be, feel free to give the video a like. And if you'd like to help other space enthusiasts discover these peaceful astronomical journeys, a subscription really does help the channel reach fellow dreamers looking for calming content to drift off to. It means the universe to me, and it helps build this wonderful community of curious minds and starlight admirers. So, find your most comfortable position and let's begin, because tonight we're going to witness something that's already happening, but which you've never noticed. We're going to trace the opening moves of a war that's been underway for millions of years. We're going to discover the wounds that are already accumulating in our galaxy, the scars that are forming in the darkness, the slow violence of gravitational attraction operating across distances that seem safe but aren't. This is a story about invisible influence, about forces that operate too slowly for human perception but too powerfully to be ignored, about how something can be both 4 billion years away and already here, both distant future and immediate present, depending on which part of the galaxies you're looking at and what time scale you're using to measure change. The collision between Andromeda and the Milky Way isn't a single event that will happen at a specific moment. It's a process, a long, patient unfolding of gravitational consequences that spans billions of years from start to finish. And we're not standing outside that process, safely removed, watching it approach from a distance. We're inside it, living through its earliest stages, experiencing the opening act of a transformation that will take longer than Earth has existed and will end long after our sun has died. Tonight, we're going to learn to see what's already happening, to recognize the signs of collision that surround us, that have always surrounded us, that we simply never knew how to interpret. Stellar streams that are actually tidal debris, gas clouds moving at impossible velocities, warped galactic disks that show the strain of external influence, dark matter halos already interpenetrating, already mixing, already beginning the slow merger that precedes the visible fireworks by billions of years. This is the war you can't see, the collision that's been underway since before our species existed, that will continue long after we're gone, that operates on timescales so vast it becomes almost meaningless to call it a collision at all. It's more like a slow fall, a gradual embrace. Two massive objects caught in each other's gravitational grip, spiraling together through the darkness with the patience of continental drift and the inevitability of entropy. And here's what makes this unsettling rather than merely interesting. Once you learn to see it, once you understand how to recognize the signs, you can't unsee it. That faint smudge in the autumn sky stops being a distant neighbor and becomes something already reaching for us, already touching us, already wounded and wounding in return. The space between galaxies stops being empty and becomes a battlefield where dark matter streams clash and stellar debris marks the casualties. The future stops being safely distant and becomes entangled with the present in ways that make the distinction between now and then feel artificial, human, imposed on a universe that doesn't recognize the boundary. So settle in, get comfortable, and let's discover together how galactic collisions really work. Not as future events, but as processes already underway. Not as distant threats, but as present realities. Not as things that will happen, but as things that are happening, slowly and invisibly, in the darkness all around us. The war you can't see has been raging for millions of years. Tonight, we learn to recognize its signs. Let's start with something that sounds almost absurdly small. Right now, at this very moment, the gravitational pull that Andromeda exerts on you, on your body, sitting or lying wherever you are, produces an acceleration of approximately 1 nanometer per second squared. A nanometer is 1/1000th of a meter, roughly the width of a few atoms lined up in a row. Per second squared. That's not just small, that's almost offensively small. That's the kind of number that makes you want to wave your hand dismissively and say, that doesn't matter, and move on to something more interesting. And you'd be right to feel that way if we were talking about human time scales. If we were talking about your lifetime, or your children's lifetimes, or the entire span of recorded human history. 1 nanometer per second squared is nothing. It's less than nothing. It's so far below the threshold of measurement that it might as well not exist. The gravitational pull from the lamp across the room affects you more. The person sitting next to you on the bus exerts more gravitational influence. That bee flying past your window in summer has a stronger gravitational effect on you than Andromeda does. But here's the thing about gravity that makes it different from almost every other force in the universe. It never stops. It never rests. It never says, okay, I've pulled enough for today, time to take a break. Gravity is the most patient force in nature, and patience given enough time becomes power. Isaac Newton figured this out more than 300 years ago, and the equation he gave us is so simple it almost seems insulting. The force of gravity between two objects equals the gravitational constant times the product of their masses, divided by the square of the distance between them. F equals g times m1 times m2 divided by r squared. That's it. That's the whole thing. No complicated terms, no special conditions, no exceptions or exclusions. And buried in that simplicity is something profound. The force never reaches zero. Never. No matter how far apart you put two objects, no matter how much distance you place between them, they still attract each other. The force gets weaker as distance increases. It drops off with the square of the distance, meaning if you double the distance, the force becomes 4 times weaker. But it never quite disappears. It approaches zero asymptotically, getting smaller and smaller, but never actually arriving at nothing. Put two atoms at opposite ends of the observable universe, and they're still pulling on each other, infinitesimally, unmeasurably, but pulling nonetheless. Gravity's reach extends to infinity. Every object with mass attracts every other object with mass. Everywhere. Always. Forever. The universe is a vast web of mutual attraction, everything pulling on everything else across the darkness, and the only question is whether the pull is strong enough to matter on timescales we care about. For Andromeda and the Milky Way, separated by 2.5 million light-years, the pull, right now, today, is weak. 1 nanometer per second squared, remember? Almost nothing. But that's the pull on you, a single human body containing perhaps 70 kilograms of matter. Scale that up to the entire Milky Way, 1 trillion solar masses, 200 billion stars, vast clouds of gas and dust, and all that invisible dark matter scaffolding, and the force becomes rather more significant. The Milky Way and Andromeda are pulling on each other with a force that's measurable, calculable, and entirely inescapable. And they've been doing it for billions of years, since both galaxies formed in the early universe, since the first stars ignited in their cores, since everything we know began. The pull has been there, patient and persistent, accumulating its effects one imperceptible increment at a time. Let's talk about what accumulating means in this context. Imagine you're pushing a shopping cart across a parking lot. You apply a force, the cart accelerates, you cover distance. Simple, immediate cause and effect. Now imagine that instead of pushing with your normal strength, you push with 1/billionth of your normal strength. The cart barely moves. Barely. You'd have to watch it with precision instruments to see any motion at all. But it is moving. Just incredibly slowly. Now imagine you keep pushing with that tiny force for 1,000,000 years. Just keep applying that 1/billionth strength push, consistently, every second, every minute, every hour, every day, for 1,000,000 years. The cart, assuming it doesn't encounter any friction or obstacles, would eventually be moving quite fast. Not because the force was strong, but because it never stopped. The velocity accumulates. The distance travelled accumulates. What was negligible in the short term becomes significant, becomes dominant in the long term. That's what's happening with Andromeda and the Milky Way. The gravitational force between them right now is weak, but it's been acting for billions of years, and it will continue acting for billions more, and over those timescales, the effects accumulate into something you can't ignore. The galaxies aren't just sitting at 2.5 million light-years separation, static and unchanging. They're falling toward each other, right now, have been for longer than Earth has existed, will continue falling until they meet. The current approach velocity is about 110 kilometers per second. That's not from a single moment of acceleration. That's the accumulated effect of billions of years of gravitational attraction. Every year, that tiny force adds a little more velocity. Every 1,000,000 years, a little more. The fall speeds up, gradually, patiently, following mathematical laws that care nothing for our perception of what constitutes significant force. Ancient Chinese philosophy understood something about invisible forces shaping reality. Feng shui, literally wind and water, is often dismissed in the West as superstition, but at its core is a sophisticated understanding that invisible influences matter, that subtle environmental factors accumulate effects over time, that what you can't see can still shape what you experience. The placement of a building, the flow of energy through a space, the arrangement of objects, all of it supposedly influencing outcomes in ways too subtle to measure directly, but real nonetheless. Whether you believe in feng shui as practice or not, the principle is sound. Invisible forces shape reality. Gravity is the universe's feng shui, the invisible influence that arranges matter across space, that determines which objects fall toward each other and which escape into isolation, that sculpts the large-scale structure of everything. And like feng shui, gravity's effects are often most powerful when they operate slowly, accumulating influences over long periods, rather than producing immediate, obvious results. There's a concept in chaos theory called the butterfly effect, the idea that a butterfly flapping its wings in Brazil could theoretically set off a chain of events that leads to a tornado in Texas. It's become a cliché, a shorthand for how small causes can have large effects in complex systems, but it's often misunderstood. The butterfly effect isn't really about butterflies or tornadoes. It's about sensitivity to initial conditions, about how tiny differences in starting points can lead to vastly different outcomes given enough time and enough complexity. The gravitational attraction between Andromeda and the Milky Way 4 billion years ago, when both galaxies were younger, when the first complex life was just beginning on Earth, was even weaker than it is today, because they were slightly farther apart. But that tiny initial attraction set in motion a process that's been accumulating ever since. Every second of gravitational pull added to every other second. Every year built on every previous year. 4 billion years of patient accumulation, of effects compounding on themselves, of tiny forces adding up to inevitable merger. And here's where it gets unsettling. The force isn't just pulling both galaxies toward each other as point masses, it's pulling differently on different parts of each galaxy. Gravity is a differential force. It depends on distance, and different parts of an extended object are at different distances from the source of gravitational pull. This creates tidal forces, the same kind of forces that raise ocean tides on Earth in response to the Moon's gravity. The side of Earth facing the Moon feels slightly stronger gravity than Earth's center does. The side facing away from the Moon feels slightly weaker gravity than the center. This difference, this differential pull, creates bulges in the ocean, pulling water toward and away from the Moon, creating the tides we see at beaches. The effect is small because the Moon is small and Earth is relatively rigid, but it's there, measurable, real. Now scale that up to galaxies. Andromeda's gravity pulls on every part of the Milky Way, but it pulls slightly harder on the side facing Andromeda and slightly softer on the side facing away. This differential creates tidal forces across our entire galaxy. Not ocean tides, stellar tides, gas cloud tides, dark matter tides. The entire galaxy is being stretched very gently by Andromeda's gravitational influence, and has been for billions of years, and will be for billions more, with increasing intensity as the distance decreases. Right now, those tidal forces are extraordinarily weak. You could model the Milky Way as a perfectly rigid object, and the tidal stress wouldn't be enough to deform it measurably. But galaxies aren't rigid. They're dynamic systems of stars and gas clouds and dark matter particles, all loosely bound together by mutual gravity, all capable of responding to external forces if given enough time. And 4 billion years is a lot of time. The outer edges of our galaxy, the stars and gas clouds at the very periphery, the ones farthest from the galactic centre and closest to Andromeda, are already feeling measurable effects. Their orbits are being perturbed, not dramatically, not in ways that would be obvious if you were somehow watching from outside, but perturbed nonetheless. The gravitational field they're moving through isn't purely from the Milky Way anymore. It's from the Milky Way plus a small contribution from Andromeda, and that small contribution is enough to change trajectories over millions of years. This is the first whisper of the collision, not loud, not obvious, not something that produces dramatic visible changes or causes immediate catastrophe, just a whisper, a subtle alteration in the gravitational environment, a gentle push that accumulates over time, the way water shapes stone, not through force but through patient, persistent contact. Drip by drip, year by year, the rock doesn't notice any individual drop, but given enough time, given enough accumulated influence, the stone is carved into shapes it never chose, following patterns determined by forces too subtle to resist at any given moment, but too persistent to ignore over the long term. Humans evolved to detect immediate threats, predators, falling rocks, storms, things that could kill us on timescales of seconds or minutes. We're extraordinarily good at recognizing and responding to sudden danger. Show us a snake and our nervous system reacts before conscious thought can catch up. That's survival. That's why we're still here after millions of years of evolution. But we're terrible at detecting slow-moving threats. Processes that operate over years or decades or centuries. Climate change, soil erosion, the gradual poisoning of groundwater. Our brains aren't wired to see these as dangers because our ancestors never needed to. A threat that takes 1,000 years to manifest isn't a threat in evolutionary terms. You'll be dead long before it matters. And so will your children and grandchildren. Evolution optimizes for the immediate, not the eventual. This is why the gravitational collision between Andromeda and the Milky Way feels abstract, even after you understand it intellectually. 4 billion years. That's not a timescale human minds can grasp in any meaningful way. It's too far beyond our experience, too removed from the threats we evolved to recognize, and 1 nanometer per second squared? That's not a force human senses can detect. It's buried so far below our perceptual threshold that it might as well not exist. But it does exist, and it's real, and it matters. The fact that we can't feel it doesn't make it less significant. It just makes it harder to take seriously. This is the first wound of the collision, not a dramatic injury you can point to, but a subtle alteration in the gravitational environment that will accumulate over billions of years into dramatic transformation. The ancient Greeks had the Moirai, the 3 fates, who controlled human destiny through the metaphor of thread. Clotho spun the thread of life, Lachesis measured it, and Atropos cut it when the time came. The thread was invisible, metaphorical, but the control was absolute. Your fate was woven before you were born. You could struggle, could try to escape, but the thread was already measured, the cutting already scheduled. The Moirai represented a particular kind of terror, the invisible force determining outcomes, the influence you can't see but can't escape. Gravity is the universe's version of the Moirai. It spins threads between every object with mass. It measures the distance and calculates the force, and eventually, inevitably, it brings objects together or pushes them apart according to mathematical laws that don't care about your preferences. The thread connecting Andromeda and the Milky Way was spun billions of years ago, The length has been measured by physics. An atropos, if we want to anthropomorphize the inevitable, is patient but certain. There's something almost meditative about forces this patient, isn't there? Something that demands a different kind of attention than the immediate and urgent. You can't watch gravity the way you watch a storm approach. You can't feel it the way you feel heat from a fire. You have to understand it mathematically, trace its effects over timescales that dwarf human experience, accept that invisible influence accumulating in darkness is just as real as visible force applied in light. Right now, tonight, as you settle towards sleep, Andromeda is pulling on every atom in your body. 1 nanometer per second squared, almost nothing. But it's been pulling on every atom in Earth for 4.5 billion years. It's been pulling on every star in the Milky Way for even longer. The force is weak, but the duration is infinite. And over infinite duration, even the weakest force accumulates effects that can't be ignored. This is gravity's first whisper. Not the obvious violence of collision, but the subtle alteration of trajectories. Not the dramatic finale, but the quiet opening. Not the scream, but the whisper. And whispers, if you listen long enough, if you give them enough time to echo and build and accumulate in the darkness, can eventually become roars. The war you can't see has opened with a whisper. Patient, persistent, accumulating its effects 1 nanometer at a time. And we're living through it, generation by generation, completely unaware of the force that's been shaping our galactic future since before Earth existed, that will continue shaping it long after we're gone, that operates on timescales so vast it makes human history look like a single breath in an endless conversation between massive objects falling slowly through the dark. We need to talk about dark matter again, because in our previous journeys together we learned something unsettling that becomes crucial now. The Milky Way's dark matter halo extends roughly 2 million light-years from our galactic center. Andromeda's dark matter halo extends roughly 2 million light-years from its center, and the distance between our centers is 2.537 million light-years. The mathematics is straightforward, even if the implications are uncomfortable. The halos don't just touch, they overlap. They've been overlapping for millions of years, possibly billions. This isn't speculation or theoretical modeling. This is what the measurements tell us, what the observations confirm, what the simulations consistently reproduce. We're not approaching the point where the halos will touch. We're past that point. We've been past it for longer than our species has existed. The dark matter structures surrounding both galaxies, the invisible scaffolding that contains most of both galaxies' mass, are already interpenetrating in the space between. And here's where dark matter's strangeness becomes important in ways we didn't need to worry about before. Dark matter doesn't collide, not in any normal sense of the word. Regular matter, the atoms that make up stars and planets and you and me, interacts through electromagnetic forces. When two atoms get close to each other, their electron clouds repel. They bounce off each other. They create heat, pressure, shock waves, collision in the ordinary sense. Dark matter doesn't do any of that. Dark matter particles, whatever they actually are, and we still don't know with any certainty what dark matter is made of, don't interact electromagnetically. They don't have electric charge, they don't feel electromagnetic forces. They pass right through regular matter as if it wasn't there, and they pass right through each other the same way. Two clouds of dark matter can occupy the same space simultaneously, their particles intermingling like two groups of ghosts walking through the same room, completely oblivious to each other's presence except for one thing: gravity. Dark matter has mass, Mass creates gravity, and gravity affects everything with mass, regardless of whether there are any other interactions. So, when the dark matter halos of the Milky Way and Andromeda overlap, the dark matter particles don't collide or bounce or create dramatic fireworks. They just flow through each other, each particle following its own trajectory through the combined gravitational field created by the total mass of both halos. Imagine two swarms of bees flying through each other. Each bee follows its own path, responding to its own internal navigation, mostly ignoring the other bees. The swarms interpenetrate. They occupy the same airspace. And after they pass through each other, the swarms are slightly mixed. Some bees from swarm A are now among swarm B and vice versa. That's roughly what's happening with the dark matter halos, except instead of bees you have particles that don't interact except through gravity, and instead of airspace you have a volume of space hundreds of thousands of light years across. Computer simulations of this process are fascinating and slightly unnerving to watch. Astronomers model millions or billions of dark matter particles as points with mass, calculate the gravitational forces between every particle and every other particle, then let the simulation evolve forward through time. You can watch the halos approach each other, overlap, interpenetrate. The particles flow through each other in complex patterns, creating streams and wakes and filaments of slightly higher or lower density. The halos don't merge smoothly like two drops of water becoming one. They mix chaotically, like two clouds of smoke in turbulent air. Some regions end up with higher dark matter density because particles from both halos have accumulated there. Other regions end up depleted because particles have flowed away. The gravitational field becomes lumpy, asymmetric, impossible to describe with simple equations. You need computers to track what's happening, need sophisticated algorithms to follow the motion of millions of particles all pulling on each other simultaneously. And here's what those simulations show consistently. The overlap creates structure. Dark matter particles streaming between both galaxies form filaments, threads of slightly higher density connecting the two halos like bridges across the void. These aren't solid structures. Dark matter is far too diffuse for that. But they're real gravitational features, regions where dark matter has accumulated in response to the combined pull of both galaxies. Think of it like water draining from a bathtub. The water doesn't drain uniformly, it forms a vortex, a spiral pattern created by the rotation and the pull of gravity toward the drain. The pattern is emergent, arising from simple physical laws applied to many particles, but it's real and reproducible. The dark matter between Andromeda and the Milky Way does something similar, forming patterns in response to the gravitational landscape created by two massive objects influencing each other. Medieval Christian theology imagined battles between angels and demons occurring in the invisible realm, in the spiritual dimension that coexisted with the physical world but remained hidden from mortal sight. These were cosmic conflicts with stakes as high as the fate of souls, waged with spiritual weapons in territories humans couldn't access or perceive. The battles were real, at least within the theological framework, but invisible, leaving only indirect evidence in the physical world through their effects on human behavior and events. The dark matter interaction between Andromeda and the Milky Way has that same quality of invisible warfare. It's happening in a realm we can't access directly, fought with weapons we can't see, gravity instead of swords, mass instead of armies. But it's real, and it's leaving evidence. The evidence is in stellar streams we'll discuss in the next chapter, in the warped structure of both galactic disks, in the orbits of satellite galaxies caught between two gravitational wells. The invisible battle shapes the visible consequences, just like those medieval theologians claimed about spiritual warfare. Border zones in mythology are dangerous places, the threshold between inside and outside, the boundary between village and wilderness, the shoreline where land meets sea. These liminal spaces, neither one thing nor fully the other, are where strange things happen, where normal rules don't quite apply, where danger and opportunity intermingle. Every culture has stories about these borders, spirits that haunt crossroads, demons that wait at doorways, gods that guard thresholds. The border is dangerous precisely because it belongs fully to neither realm, subject to influences from both, stable in neither. The overlap zone between Andromeda's halo and the Milky Way's halo is a cosmic border zone. It's not clearly Andromeda's territory, and not clearly ours. It's contested space, subject to gravitational influence from both galaxies, stable only in the sense that the chaos has reached equilibrium. Any object in that zone, a satellite galaxy, a cloud of gas, a stream of stars, feels competing pulls, experiences a gravitational environment that's complex and variable and difficult to navigate. And that's where the casualties will appear first. Not in the hearts of either galaxy, where one gravitational influence dominates clearly, but in the border zone, where objects are torn between competing attractions, where the gravitational field is strongest from one galaxy at some times and from the other galaxy at other times, where predictable orbits become unstable and small perturbations accumulate into catastrophic changes. We can calculate something called the tidal radius, the distance from a galaxy's center where its gravitational influence becomes comparable to the influence of neighboring galaxies. Inside the tidal radius, the galaxy dominates. Outside, external forces become significant. For isolated galaxies, the tidal radius can extend to enormous distances because there aren't any nearby competitors. For galaxies in clusters or groups, the tidal radius is smaller because neighbor galaxies restrict each other's gravitational domains. For Andromeda and the Milky Way, the tidal radii are shrinking. As they fall closer together, as their mutual gravitational influence increases, the distance at which each galaxy's pull dominates decreases. The border zone grows larger. More and more space falls into that contested territory where neither galaxy has clear gravitational authority, where objects experience competing attractions, where stability gives way to chaos. Think of two countries at war, each one controlling territory, each one defending borders. But as the conflict progresses, the front lines shift and the border zone expands. The safe interior of each country shrinks. More civilians find themselves in contested territory, subject to raids from both sides, unable to rely on the protection of either government. That's what's happening gravitationally in the local group. The safe interior of each galaxy, the region where objects can orbit peacefully undisturbed by external influence, is shrinking as the border zone expands. The Norse had a concept called Ginnungagap, the primordial void that existed before creation, the gap between Niflheim, the world of ice, and Muspelheim, the world of fire. Ginnungagap was emptiness, but it was also the space where creation happened, where fire and ice met, and from their interaction came the first life, the first beings, the raw material of the cosmos. The void between wasn't truly empty. It was the space where opposing forces mixed, where new things could emerge from the tension between opposites. The space between Andromeda and the Milky Way is our Ginnungagap. It looks empty. It's mostly vacuum, with just occasional atoms of hydrogen and helium drifting in the intergalactic medium. But it's not empty gravitationally. It's full of dark matter from both halos, streaming and mixing. It's full of gravitational influence from both galaxies. It's the void where two massive structures are already beginning to interact, already creating the conditions that will eventually transform both. And here's what makes this particularly unsettling. We're in it. Not at the centre of the overlap zone. We're closer to the Milky Way's centre than Andromeda's, so we're still clearly in our galaxy's territory, but the overlap zone extends inward. Dark matter from Andromeda's halo reaches past our position. We're swimming in gravitational influence from both galaxies, even if the Milky Way's influence dominates locally. The border has already reached us. We just didn't know how to recognize it until recently. This is the philosophical challenge of invisible influence. How do you come to terms with forces you can't detect directly? How do you accept that something imperceptible is real and significant? The history of science is full of this kind of challenge. Germs were invisible until we invented microscopes, but they were always real, always causing disease, always shaping human history through plague and pandemic. Radio waves were undetectable until we built receivers, but they were always there, always propagating through space, always available for anyone who developed the technology to notice them. Dark matter is the same. It's been here all along, making up most of the universe's mass, shaping galactic structures, determining the fate of cosmic evolution. We just couldn't see it, couldn't detect it directly, couldn't measure it except through its gravitational effects. And now that we know it's there, now that we've traced the halos and mapped the overlap and understood the implications, we have to accept that our galactic address is more complicated than we thought. We're not just in the Milky Way. We're in the Milky Way, which is gravitationally bound to Andromeda, whose halos overlap, creating a border zone that extends through our position in space. We're in contested territory, cosmically speaking, under siege from forces we can't see. Caught in the opening stages of a gravitational war that will take billions of years to play out, but which has already begun in the dark matter flowing through the space around us. Dark matter particles are passing through your body right now, trillions of them, every second streaming through the Earth and through you as if you weren't there. Some of those particles belong to the Milky Way's halo. They've been orbiting our galaxy for billions of years, part of the invisible scaffolding that holds us together. But some of them belong to Andromeda's halo. They're visitors, scouts, advanced particles that have ventured across the gap between galaxies and now flow through our space on their way to whatever trajectory the combined gravitational field dictates. You can't feel them. They interact so weakly with normal matter that they might as well be ghosts. But they're real, they're here, and they're part of the evidence that the collision has already begun. The border between galaxies isn't where the stars end. It's not where the visible light fades to darkness. It's somewhere in the middle of the overlap zone, in a region of space where dark matter from both galaxies mixes and mingles and creates the complex gravitational landscape that will eventually tear both structures apart and rebuild them into something new. There's something deeply unsettling about invisible intimacy, isn't there? About discovering that something you thought was separate and distant is actually already touching you, flowing through you, influencing your environment in ways you never noticed. Like discovering that your house has had foundation cracks for years, slowly widening, invisible beneath the surface, creating structural problems that will eventually manifest, but which you couldn't see because you were only looking at the walls and roof. The dark matter entanglement between Andromeda and the Milky Way is that foundation crack. It's been there for millions of years, possibly billions, growing slowly, spreading invisibly, creating stress and strain in both galactic structures, and we've only just learned to look beneath the surface, to trace the invisible architecture, to recognize that the border between galaxies dissolved long ago in everything except the visible light we've been using to define boundaries. The war you can't see is being fought in dark matter, in the gravitational realm, in the invisible majority of both galaxies that doesn't shine but dominates. And that war has already reached us, already surrounds us, already defines our gravitational environment, even though we can't feel it, even though it operates on timescales that make human history irrelevant, even though it will take billions of years to produce visible consequences. The halos are entangled, the border is contested, the overlap zone is expanding as both galaxies fall closer together, and we're living in the crossfire, in the space where two massive invisible structures are beginning their slow, patient, inevitable merger, one dark matter particle at a time, one gravitational influence at a time, one imperceptible change accumulating on top of every other imperceptible change, until eventually the accumulated weight of invisible warfare produces visible transformation. The dark matter knows the collision has already begun. It's flowing and mixing and streaming between both galaxies even now. We're just catching up to what's been true all along, learning to see the invisible battle that's been raging in the darkness around us, since before we learned to look up at stars and wonder what they were. If you want to find evidence of violence, you don't look at the warriors. You look at what they left behind, the debris field, the scattered remains, the traces that persist after the conflict has moved on, and in the space around both the Milky Way and Andromeda. If you know what to look for, if you have the right instruments and the patience to search, you can find the casualties. Not dramatic explosions or sudden catastrophes, but slow dissolving, patient destruction, the gradual tearing apart of smaller galaxies that had the misfortune to orbit too close to giants engaged in their own slow collision. These casualties have a name: stellar streams, long thin ribbons of stars stretching across the sky, visible only in careful surveys that map millions of individual stars and trace their positions and velocities. They're the ghosts of dead galaxies, the remains of structures that once existed as coherent objects but have been pulled apart by tidal forces, scattered along their orbital paths, like cosmic breadcrumbs marking the place where something ceased to exist as a unified whole. Let's talk about how this happens, because the mechanism is both elegant and brutal in its simplicity. Imagine a small satellite galaxy. Nothing massive, maybe a few billion stars, perhaps a dwarf spheroidal, or an irregular galaxy, something that would barely qualify as a galaxy if it weren't orbiting a larger structure. This small galaxy has its own internal gravity holding it together, its stars orbiting around its center of mass, maintaining something like coherence even though it's small and unimpressive compared to the giants it orbits. Now put that small galaxy in orbit around something like the Milky Way or Andromeda. The satellite feels the gravitational pull from the larger galaxy, which is what keeps it in orbit in the first place. But here's the crucial detail: different parts of the satellite galaxy feel slightly different amounts of gravitational pull. The side facing the larger galaxy feels stronger gravity than the far side, because it's closer to the source. This differential pull, this tidal force, creates stress across the satellite galaxy. If the satellite is massive enough, if its own internal gravity is strong enough, it can resist the tidal stress. It stays together, orbiting peacefully, maintaining its structure. But if the tidal stress exceeds the satellite's self-gravity, if the differential pull becomes stronger than the force holding the satellite together, something dramatic happens. The satellite starts to dissolve. Stars on the leading edge of the orbit, pulled harder by the larger galaxy's gravity, drift ahead. Stars on the trailing edge, pulled less strongly, lag behind. The satellite stretches along its orbital path like taffy being pulled, transforming from a compact object into a long, thin stream of stars. Over millions of years, over multiple orbits, the satellite completely dissolves. What was once a galaxy, a coherent structure with its own identity, its own history, becomes a stream of stars following roughly the same orbit, but no longer bound together, no longer recognizable as a unified object. The galaxy has been murdered by tidal forces, its body scattered along the orbital path, leaving only this thin trail of stars as evidence that it once existed. And here's the thing that makes this relevant to the collision between Andromeda and the Milky Way. Both galaxies are surrounded by these stellar streams. Multiple streams, in fact. The more carefully we look, the more we find. Each stream represents a satellite galaxy that was captured, that orbited one of the giants, and that was eventually torn apart by tidal forces and scattered into stellar debris. Each stream is a casualty. Each stream is evidence that both galaxies are already violent, already destructive, already in the business of consuming smaller neighbours. The Milky Way's most prominent stream is the Sagittarius stream, the slowly dissolving remains of the Sagittarius dwarf elliptical galaxy. This small galaxy has been orbiting the Milky Way for billions of years, gradually losing stars with each pass through our galactic disk. Computer simulations and careful observations show that the Sagittarius galaxy has wrapped around the Milky Way multiple times, creating loops of stars above and below the galactic plane, leaving a trail that astronomers can trace across the entire sky. The galaxy that's creating this stream is still there. You can still identify a central concentration of stars, still measure its orbit, still call it a galaxy if you're generous. But it's dying, dissolving, being pulled apart by our galaxy's tidal forces. In a few more orbits, it will be gone entirely, reduced to nothing but a thin stream of stars marking where it used to be. Then there's the Monoceros ring, a controversial structure that appears as a ring of stars surrounding the Milky Way's disk. Some astronomers think it's the remains of another disrupted dwarf galaxy, tidal debris wrapped around our galaxy like ribbons around a present. Others argue it might be part of the Milky Way's disk that's been warped and pulled outward by gravitational interactions. The debate continues, but regardless of which interpretation is correct, the Monoceros ring is evidence of disruption, of structures being pulled and stretched and deformed by gravitational forces operating over enormous timescales. Gaia, that spacecraft named for the Earth goddess, the one that's been measuring the positions and velocities of billions of stars with extraordinary precision, has revealed even more streams in recent years. Streams we didn't know existed, because they're too faint, too diffuse, too thoroughly scattered to have been detected by earlier surveys. Each new data release from Gaia brings discoveries of new streams, new evidence of disrupted satellites, new casualties in the gravitational warfare that surrounds our galaxy. Andromeda has its own collection of streams, and some of them are spectacular. The giant stellar stream, discovered in the early 2000s, wraps around Andromeda like a cosmic scarf, extending for hundreds of thousands of light years, containing the remains of what must have been a substantial dwarf galaxy before Andromeda's tidal forces tore it apart. Astronomers have traced other streams around Andromeda as well, each one representing another satellite that orbited too close, that felt tidal forces stronger than its self-gravity, that dissolved slowly over billions of years into stellar debris. These streams tell us something important. Both Andromeda and the Milky Way are already violent. They've been consuming smaller galaxies for as long as they've existed. This is how large galaxies grow, not just through internal star formation, but through cannibalism, through capturing smaller satellites and slowly absorbing their mass. It's galactic imperialism, cosmic empire building through conquest and consumption, and it's been happening constantly throughout the entire history of both galaxies, long before they started their approach toward each other. But here's where the collision becomes relevant. As Andromeda and the Milky Way fall closer together, the satellite galaxies orbiting both giants find themselves caught in an increasingly complicated gravitational environment. A satellite that once orbited peacefully around Andromeda, feeling primarily Andromeda's gravitational influence, now also feels the Milky Way's pull. The tidal stresses increase, the orbital dynamics become unstable. What was survivable becomes lethal. Medieval history is full of small kingdoms caught between great powers, the Italian city-states during the wars between France and Spain, the Eastern European nations caught between Nazi Germany and the Soviet Union, the Korean Peninsula between China and Japan. These small entities often had no agency in the larger conflicts. They were simply in the wrong place at the wrong time, situated geographically between empires that wanted to destroy each other, suffering the collateral damage of wars they didn't start and couldn't prevent. The satellite galaxies around Andromeda and the Milky Way are in that same position. M32 and M110, Andromeda's two most prominent companions, are small elliptical galaxies that have orbited Andromeda for billions of years. They've survived this long, presumably, because they're massive enough and far enough from Andromeda's centre that tidal forces haven't torn them apart yet. But as the Milky Way approaches, as the combined gravitational field becomes more complex, their futures become uncertain. Computer simulations suggest that at least one of them will likely be destroyed during the merger, torn apart by the combined tidal stress from both giants. The Magellanic Clouds, those two irregular galaxies visible from Earth's southern hemisphere, the Large Magellanic Cloud and the Small Magellanic Cloud, are our own satellite galaxies, and they face similar uncertainty. They orbit the Milky Way at distances of about 160,000 and 200,000 light-years, close enough that they're well within our gravitational domain, but also close enough to the overlap zone with Andromeda's halo that they'll eventually feel competing influences. Some simulations suggest the Magellanic Clouds might be stripped of their gas during the merger, their star formation shut down by the violence of the collision even if their stellar populations survive. Other simulations show them being ejected from the system entirely, flung into intergalactic space by gravitational slingshot effects. We don't know for certain what will happen to any of these satellites. The outcome depends on precise details of orbital parameters, on the exact trajectory of the Andromeda-Milky Way collision, on timing and position at critical moments. Small changes in initial conditions lead to dramatically different fates. But we do know that they're at risk, that they're casualties waiting to happen, that they're caught in the crossfire of something much larger than themselves. There's a particular melancholy in stellar streams that hits differently than other cosmic structures. When you look at an active galaxy, at a spiral with bright arms and vigorous star formation, you're looking at something alive, something continuing, something in the midst of its story. When you look at a stellar stream, you're looking at a corpse, an echo, a trace of something that once existed but doesn't anymore. The stars are still there. Stars have lifetimes measured in billions of years, so the individual stars in a disrupted satellite can persist long after the satellite itself has dissolved. But they're orphaned now, no longer part of any coherent structure, just drifting through space following the orbital path that was determined when their parent galaxy was torn apart. Australian Aboriginal cultures have concepts of ancestral traces in the landscape. sacred sites that mark places where ancestral beings walked during the dreamtime, where important events occurred, where the spiritual realm touched the physical. These aren't just historical markers, they're living connections to the past, places where the ancestral presence still exists in some sense, where what happened long ago continues to resonate in the present. The landscape is read as a text written by the ancestors, and learning to see those traces is learning to understand the deeper reality beneath the surface. Stellar streams are our cosmic version of ancestral traces. They're marks left in the structure of space around both galaxies, evidence of events that happened millions or billions of years ago, connections to a past when these satellites existed as coherent structures before they were consumed. And learning to see the streams, learning to detect them in Gaia data, learning to trace their orbits and reconstruct their histories, is learning to read the landscape of our galactic neighborhood, understanding the violence that's been occurring for eons before we develop the capacity to notice it. The Norse described Ragnarok, the end of the world, as a cataclysmic battle that would shatter the realms and leave only wreckage. After the final battle, after the gods fell and the world burned, there would be debris scattered across the cosmos, shattered realms, broken weapons, the remains of a world that once was. And from that debris, according to the myth, a new world would eventually emerge, built from the ruins of the old. The destruction wasn't the end. It was the clearing away that enabled new creation. Stellar streams have that same quality of wreckage from which new things will be built. The stars that currently drift in streams around both galaxies will eventually be incorporated into Milkomeda. They'll find new orbits in the merged galaxy, become part of the stellar halo, contribute their mass to the new structure. The satellites that created them died, yes, were destroyed, scattered, dissolved into constituent stars. But the matter persists, the stars continue. What was lost was the pattern, the organization, the temporary coherence that made those satellites recognizable as separate entities. The substance remains, ready to be incorporated into whatever comes next. This is the first clear evidence that the collision has already produced casualties. Not in the future, not when the visible parts of Andromeda and the Milky Way finally crash together, but already, now, in the present. The stellar streams we can observe in both galaxies, the disrupted satellites being torn apart by tidal forces, the increasingly complex gravitational environment that's making formerly stable orbits unstable. All of this is evidence that the collision has effects that precede the dramatic finale by billions of years. The small galaxies are always the first to go, always. In every galaxy merger we observe across the universe, in every collision between massive systems, the satellites and dwarf galaxies are disrupted first, torn apart by tidal forces that strengthen as the giants approach each other. They're the warning signs, the canaries in the cosmic coal mine, the indicators that gravitational stress is increasing even when the main galaxies still look peaceful and undisturbed. There's something profoundly unfair about this, isn't there? The small galaxies didn't choose to orbit near giants engaged in slow collision. They formed where they formed, fell into orbits determined by the gravitational environment of the early universe, and now they're being destroyed as collateral damage in a conflict that has nothing to do with them. They're bystanders suffering the consequences of forces beyond their control, torn apart by gravitational stress that wouldn't exist if the two large galaxies weren't falling toward each other. But the universe doesn't care about fairness. It doesn't care about intentions or agency, or whether destruction is deserved. It just follows physical laws with perfect consistency, and those laws say that small objects orbiting near massive objects in complex gravitational environments will be torn apart by tidal forces. The math doesn't care. The physics doesn't care. The satellites dissolve into streams not because they did anything wrong, but because they were in the wrong place at the wrong time, caught between gravitational giants. So when you look at the night sky, when you see the Magellanic Clouds, if you're lucky enough to be in the southern hemisphere, know that you're looking at casualties in waiting. They're still intact now, still recognizable as galaxies, still maintaining their coherence, but they're living on borrowed time, orbiting in an increasingly hostile gravitational environment, waiting for the moment when tidal stresses exceed their ability to resist, and they begin their slow dissolution into stellar streams that future astronomers will detect and study and use as evidence of the collision that's happening in our era. The stellar streams are ghosts, echoes of violence already committed, traces of satellites that once existed but have been torn apart by the invisible warfare between massive gravitational fields, and they're everywhere around both galaxies once you learn to see them, once you develop the instruments sensitive enough to detect faint ribbons of stars scattered across the sky, once you understand that what looks like empty space is actually full of stellar debris marking the graves of small galaxies that got too close to giants. The first casualties are always the weak, caught in the crossfire, torn apart by forces they can't resist. The stellar streams remember them, preserve their orbits, mark the places where coherence gave way to dissolution, and we're learning to read those streams, to trace them across the sky, to understand that they're evidence of the collision that's already underway, that's already producing casualties, that won't stop producing casualties until both galaxies have merged completely, and the new gravitational equilibrium is so obvious that even the satellites, if any survive, will know exactly where they stand. There's something deeply unsettling about things that move wrong. A car driving backward on a highway, a river flowing uphill, birds flying in winter when they should have migrated months ago. These anomalies trigger something instinctive in us, some pattern recognition system that notices when reality deviates from expectation, that flags the unusual as potentially dangerous. And in the sky around our galaxy, if you have radio telescopes sensitive to hydrogen emissions at 21 centimeter wavelength, if you map the velocities of gas clouds floating through the halo, you'll find things moving wrong. Very wrong. Fast enough and in directions strange enough that they shouldn't exist if our galaxy were peacefully isolated, undisturbed, alone. These are called high-velocity clouds, HVCS in the astronomical shorthand, and they're exactly what the name suggests, clouds of neutral hydrogen gas moving at velocities that are anomalously high compared to the normal rotation of the galactic disk. Regular gas clouds in our galaxy's disk orbit at velocities determined by their distance from the galactic center, following predictable patterns set by the galaxy's mass distribution and rotation. But HVCS move at velocities that don't fit the rotation curve, don't match the expected pattern, don't make sense unless something unusual is happening. Let's talk About Smith's cloud, because it's the poster child for high-velocity weirdness, and it's heading our way. Discovered in the 1960s by Gail Smith, a graduate student at the time, one of those discoveries that happens when someone notices something odd in data that everyone else has been looking at but not really seeing. Smith's cloud is an enormous structure of neutral hydrogen gas located about 40,000 light-years from the galactic disk. It's comet-shaped, or perhaps torpedo-shaped if you prefer your metaphors more ominous, about 11,000 light-years long and maybe 2,500 light-years wide at its bluntest part. And it's approaching the Milky Way's disk at about 70 kilometers per second, not relative to us, but relative to the local standard of rest, the reference frame of gas clouds that happily orbiting the galaxy in normal, predictable ways. 70 kilometers per second doesn't sound particularly fast in cosmic terms. That's slower than Earth orbits the Sun, slower than the Sun orbits the galactic center, but it's fast compared to what gas clouds at that location should be doing. Gas in the galactic halo should be moving slowly, lazily, following gentle orbits or falling gradually toward the disk. Smith's cloud is charging toward the disk like it has somewhere important to be, like it's been thrown or pulled or pushed by forces that don't affect normal gas clouds, like it's a messenger arriving with urgent news that we don't yet know how to read. In about 30 million years, which is soon in galactic terms practically tomorrow, Smith's cloud will collide with the Milky Way's disk. Not a gentle merger, not a smooth accretion, a collision. The cloud will smash into the disk at 70 kilometers per second. The gas will shock heat to millions of degrees. The compression will trigger a burst of star formation, and the impact site will light up with newly formed massive stars and the supernovae they'll produce when they die young and violent. It will be spectacular if there's anyone around to watch. A cosmic fireworks show triggered by gas that's been falling toward us for millions of years, that we've been watching approach with radio telescopes, that we can see coming but can't do anything about, not that we'd want to, because this is how galaxies accrete material, how they add gas to their disks, how they fuel star formation and growth. But here's the question that makes Smith's cloud relevant to the collision story. Where did it come from? What kicked it into this high-velocity trajectory? Why is it moving so fast in a direction that doesn't match normal galactic rotation? There are theories, naturally. Maybe it's a leftover from the galaxy's formation, a blob of primordial gas that never quite settled into the disk and has been wandering through the halo ever since. Maybe it's gas that was ejected from the disk by supernova explosions, or by the collective stellar winds from massive stars, thrown outward with enough energy to escape the disk, but not enough to leave the galaxy entirely. Maybe it's the remnant of a small satellite galaxy that was stripped of most of its stars but retained some gas. Or maybe, and this is where it gets interesting, maybe it's tidal debris, gas pulled out of the Milky Way, or pulled off Andromeda, or the Magellanic Clouds by gravitational interactions, set into motion by forces that wouldn't exist if our corner of the universe were gravitationally simple. We don't know for certain. The uncertainties are large, the observations consistent with multiple interpretations, but the very existence of Smith's cloud and the dozens of other high-velocity clouds scattered through our galactic halo is evidence that something complicated is happening, that the gravitational environment around our galaxy isn't simple and isolated, that there are forces pulling and pushing gas into trajectories that don't match the clean picture of a spiral galaxy rotating peacefully through space. Ancient cultures read omens in clouds, the shapes they formed, the directions they moved, the colours they displayed at sunset. Roman augurs watch for specific cloud formations before important decisions. Chinese court astronomers maintained careful records of unusual clouds, interpreting them as messages from heaven about the state of the empire. Medieval Europeans saw armies fighting in the clouds, portents of coming war, angels and demons battling in the upper air. The idea that clouds carry messages, that their movement signals something about future events, is older than written history and nearly universal across cultures. High-velocity clouds are our cosmic omens. They're moving wrong, which means something is affecting them, which means the gravitational environment is more complex than it appears, which means forces are at work that we don't fully understand yet, but which manifest in anomalous gas kinematics. The clouds aren't literally sending messages. They don't have agency, don't carry information intentionally, but they're revealing something about the hidden forces shaping our galactic neighborhood, the same way smoke reveals wind patterns even when the wind itself is invisible. Let's talk about Complex C, because if Smith's cloud is a messenger, then Complex C is a delegation, possibly an invading army. Complex C is another high-velocity cloud system, much larger than Smith's cloud, covering a substantial chunk of the sky when viewed in radio wavelength maps of neutral hydrogen. It's approaching the Milky Way's disk at velocities around 100 to 150 kilometers per second, depending on which part you measure. That's seriously fast. That's wrong enough that it demands explanation, that flagged itself as anomalous as soon as astronomers mapped it, that has generated dozens of research papers trying to explain what it is and where it came from. The leading theory for Complex C is that it's material being accreted from the intergalactic medium, gas that was never part of our galaxy before but is now falling in, captured by our gravity well, adding mass to the Milky Way. If true, that's actually good news. Galaxies need to accrete gas to maintain star formation over cosmic timescales, and Complex C represents a substantial delivery of raw material. But where did it come from? Why is it falling in at such high velocity? What perturbed it out of the intergalactic medium and set it on this trajectory? One possibility, mentioned quietly in some papers but not yet proven, is that Complex C is tidal debris, gas pulled out of the intergalactic medium or out of one of the galaxies in the local group by the gravitational interactions between Andromeda and the Milky Way. The complex gravitational landscape created by two massive galaxies falling toward each other could accelerate gas clouds, could pull material from one galaxy toward another, could create exactly the kind of anomalous velocities we observe in Complex C and other high-velocity clouds. This is speculation, careful speculation backed by models and simulations but not yet confirmed by definitive observations. But it's plausible, and if true, it means that high-velocity clouds aren't just curiosities, aren't just weird features of our galactic halo that we struggle to explain. They're harbingers, early signs of the collision, evidence that gravitational interactions between Andromeda and the Milky Way are already affecting the gas distribution in the space between and around both galaxies, already pulling material into trajectories that wouldn't exist if both galaxies were isolated. There's a class of clouds called intermediate velocity clouds, IVCS, which move at velocities between normal disk rotation and the extreme speeds of high-velocity clouds. They're the transition population, the clouds that are definitely moving faster than they should, but not quite fast enough to qualify as dramatically anomalous. And here's what makes them interesting. The boundary between normal velocity gas and intermediate velocity gas is somewhat arbitrary, somewhat dependent on where you draw the line, but the fact that there's a continuum of velocities from normal to intermediate to high suggests a continuum of causes, a gradual transition from gas that's unperturbed to gas that's definitely perturbed by something external. It's like watching refugees fleeing a war zone. The ones closest to the conflict move fastest, most urgently, with the most obvious signs of disruption. The ones farther from the conflict move less urgently, but still faster than normal peacetime migration patterns. And the ones at the edge of the effect barely seem affected at all until you measure carefully and realize they're moving slightly faster than they should, responding to distant pressures that haven't reached crisis level yet, but which are definitely present. Chinese philosophy has a concept called qi, the vital energy that flows through all things, that animates living beings, that moves through the landscape and affects health and fortune and fate. Qi is invisible but real, something you can't measure with instruments but which practitioners claim to feel and manipulate and diagnose. When qi flows smoothly, health and harmony result. When qi is blocked or disrupted or flowing wrongly, disease and discord follow. And learning to sense qi flow, according to traditional Chinese medicine, is learning to diagnose problems before they manifest as obvious symptoms. High-velocity clouds are disrupted qi in the cosmic body of our galaxy. They're gas flowing wrongly, moving at velocities that indicate something is perturbed, something is affecting the normal flow patterns, and learning to read them, learning to map their velocities and trajectories, learning to trace their origins and predict their impacts, is learning to diagnose the early stages of gravitational disease, the disruption that precedes the obvious symptoms by millions or billions of years. When Smith's cloud hits the galactic disk in 30 million years, the impact will be spectacular but localized. A burst of star formation, some new stellar nurseries, a few thousand massive stars lighting up a region of the disk that was previously quiescent. The disk will survive. The galaxy will be fine. One gas cloud falling in doesn't threaten galactic stability. But Smith's cloud isn't alone. There are dozens of high-velocity clouds scattered through the halo, all of them approaching the disk at various velocities, all of them scheduled to collide over the next tens or hundreds of millions of years. It's not a single impact, it's a bombardment, a slow rain of high-velocity gas falling onto the disk from above and below, adding mass but also adding chaos, disrupting the organized rotation of the disk, injecting energy and turbulence. And that's just the high-velocity clouds we've detected so far, the ones massive enough and close enough that radio surveys have found them. There might be more smaller clouds or clouds made of ionized gas rather than neutral hydrogen, things that don't show up in 21-centimeter surveys, but which contribute to the general disruption nonetheless. The more carefully we look, the more we find, which is often how astronomy works. New instruments reveal new layers of complexity, new populations of objects that were always there but invisible to previous generations of observers. Medieval sentries watching for enemy armies didn't wait until they could see the main force approaching. They watched for scouts, for advance parties, for the subtle signs that something was coming even when the enemy was still beyond the horizon. Dust clouds in the distance, birds disturbed from their roosts, livestock acting nervous, the absence of normal travellers on the roads. You learn to read these signs not because any individual sign was definitive, but because the accumulation of anomalies meant something, meant you should prepare, meant danger was approaching even if you couldn't see it directly yet. High-velocity clouds are the scouts and advance parties of galactic collision. They're not the main event that comes in 4 billion years, when the stellar disks finally interpenetrate, but they're signs that something's coming, that the gravitational environment is already disturbed, that forces are at work pulling gas into strange trajectories and setting up the conditions for future chaos. And we're watching them approach, mapping their velocities with radio telescopes, calculating their impact times and locations, reading the omens, even though we can't do anything to change what's written in their trajectories. There's something almost meditative about watching doom approach in slow motion, knowing it's coming, but knowing it will arrive so slowly that no human lifetime will span more than a tiny fraction of the approach. You can't panic about something that takes 30 million years to arrive. You can't feel urgency about an impact that will happen thousands of generations after your death. The appropriate emotional response to high-velocity clouds isn't fear. It's something more like fascination or perhaps melancholy appreciation, the feeling you get watching a very slow sunset that you know will be beautiful when it finally completes, but which takes so long that you can't maintain active attention on it the whole time. Smith's cloud will hit the disk. Complex C will accrete. The dozens of other high-velocity clouds will rain down onto the Milky Way over the next 100 million years. Each impact will trigger star formation, will add mass to the disk, will contribute to the ongoing evolution of our galaxy. And through it all, the approach with Andromeda continues. The gravitational influence strengthens, the tidal forces increase, setting up conditions for even more gas to be pulled into anomalous trajectories, creating new high-velocity clouds, new harbingers, new messengers arriving from the darkness to tell us that the collision is still approaching, is still gathering momentum, is still playing out across timescales that make human history seem like a single breath. The clouds move wrong. That's the first thing. That's the observation that makes them worthy of attention, that marks them as anomalous, that demands explanation. And when you dig into the explanations, when you trace the possible origins and the forces that could create such high velocities, you find yourself confronting the complex gravitational environment created by two massive galaxies falling toward each other, pulling gas around, disrupting the simple picture of isolated rotation, creating exactly the kind of chaos that high-velocity clouds represent. They're harbingers, messengers, omens written in neutral hydrogen moving at 70 or 100 or 150 kilometers per second through the galactic halo, approaching the disk, carrying news of disruption and transformation, arriving from the darkness like ancient prophets arriving in the capital to announce that war is coming, that the peace was always temporary, that the enemy is already on the march, even if you can't see them yet, even if the horizon looks clear, even if everything seems normal until you look at the scouts and realize they're running, fleeing, moving faster than they should, and their speed tells you everything you need to know about what's following behind. The high-velocity clouds move wrong because something is pushing or pulling them wrong, and that something is the gravity of two massive galaxies falling toward each other across 2.5 million light-years, already affecting gas distributions, already creating tidal debris, already writing the opening chapters of a collision that won't complete for billions of years, but which announces itself through anomalous velocities in the clouds that drift through the darkness around us. If you grew up anywhere with persistent wind, you've seen what it does to trees. Not the dramatic effects of storms, those are obvious, violent, immediate, but the slow, patient work of prevailing winds blowing from the same direction year after year, decade after decade. The trees grow bent, leaning away from the wind, branches stretching downwind, trunks curved in permanent testimony to invisible force. No single gust of wind bends the tree, but thousands of days of pressure, applied consistently from the same direction, shape the growth until the bend becomes permanent, built into the structure, visible evidence of invisible influence. The Milky Way is bent, not dramatically, not in ways you'd notice if you were somehow floating outside the galaxy looking at it from above, but it's there, measurable, real, our galactic disk, that beautiful flat spiral we imagine when we picture the Milky Way, isn't actually flat, it's warped. The northern hemisphere of the disk tilts slightly upward relative to the galactic plane. The southern hemisphere tilts slightly downward. The deviation is about 5,000 light-years at the edges of the disk, which sounds like a lot until you remember the disk is about 100,000 light-years across. It's a subtle warp, a gentle S-curve in cross-section, but it's definitely there. We've mapped it using stellar positions, gas clouds, everything we can measure that traces the disk structure. And here's the question that astronomers have been arguing about for decades. Why? What causes the warp? What force or combination of forces could bend a structure as massive as a galactic disk, could distort something held together by the combined gravity of hundreds of billions of stars, could create permanent deformation in an object that should be stable, flat, organized, according to rotation and angular momentum? There are several suspects. The Magellanic Clouds, those two satellite galaxies orbiting us, exert tidal forces as they swing around the Milky Way. Their gravity pulls on our disk, especially on the outer regions where stars are more loosely bound and more susceptible to external influence. Computer simulations show that massive satellites can indeed create warps in galactic disks through repeated tidal interactions over hundreds of millions of years. The Magellanic Clouds are certainly massive enough and close enough to be relevant. They're suspects with means, motive, and opportunity. But there's another suspect, one that's farther away but much more massive, one that we've been talking about for the entire journey so far: Andromeda. At 2.5 million light-years distance, Andromeda seems too far away to warp our disk. The tidal forces at that distance are extraordinarily weak. But weak isn't the same as zero, and over billions of years, over the entire lifetime of both galaxies since they formed in the early universe, even extraordinarily weak tidal forces can accumulate effects. The Milky Way and Andromeda have been pulling on each other for longer than complex life has existed on Earth. That's a lot of time for subtle forces to shape structures. Recent studies using Gaia data that spacecraft keeps showing up, doesn't it, providing ever more precise measurements of stellar positions and motions, suggest that the warp might be dynamic, not static. It might be changing, evolving, processing around the galaxy like a wave. The northern hemisphere tilts up, but that tilt rotates slowly around the galactic center, completing a full rotation every few 100 million years. That's weird. That's not what you'd expect from a static deformation. That suggests something actively driving the warp, something continuously perturbing the disk in ways that create time-varying distortion. And when you try to model what could create that kind of dynamic warp, what forces could continuously drive precession in the disk structure, you end up needing external perturbers. The Magellanic Clouds probably contribute, but some models suggest that Andromeda's distant tidal influence, combined with the dark matter halo interactions we discussed earlier, could also play a role. The warp becomes a fingerprint of gravitational harassment, evidence that our galaxy isn't isolated and unperturbed, but is being pulled and pushed by external forces operating on timescales so long that the deformation becomes permanent, built into the structure, written in the architecture of the disk itself. Andromeda's disk is also warped, not in exactly the same way. The details differ because the gravitational environment differs, the satellite populations differ, the mass distributions differ. But there's definitely a warp there too, visible in careful mapping of stellar populations and gas distributions. Two massive spiral galaxies, both warped, both showing structural deformations that suggest external gravitational influence. That's not a coincidence. That's evidence. That's the signature of two objects pulling on each other across millions of light years, shaping each other's structure over billions of years, writing their mutual influence into the physical form of both galaxies. There's a medieval torture device called the rack. You've probably heard of it. It features prominently in historical dramas and horror stories. usually accompanied by ominous creaking sounds and the screams of victims. The principle is simple and brutal. You stretch a person by attaching their limbs to a frame and then slowly pulling. The stretching doesn't break bones immediately. That would be too quick, too merciful. Instead, it works on tendons and ligaments and joints, pulling them past their normal range of motion, creating pain that builds gradually as tissue stretches beyond its capacity to remain intact. Tidal forces are the universe's version of the rack. They work by differential gravitational pull. One end of an object feels stronger gravity than the other end, creating stress across the object's structure, and given enough time, given sufficient force applied over millions of years, tidal forces can distort even something as massive and self-gravitating as a galactic disk. The disk doesn't break. Galaxies aren't rigid structures that snap under stress, but it bends, it warps, it deforms in ways that become permanent once the stress has been applied long enough. The galaxy is being stretched by tidal forces, pulled by external gravitational fields, subjected to cosmic torture that operates too slowly to be noticed in real time, but which accumulates effects that become visible once you measure carefully enough. Buddhist philosophy has a concept called dukkha, often translated as suffering but more accurately understood as unsatisfactoriness, the fundamental sense that something isn't quite right, that there's a persistent wrongness or distortion in existence. Dukkha isn't always dramatic pain. Sometimes it's just the subtle sense that things are slightly off, that there's tension or stress or imperfection in situations that should be comfortable. The human condition includes dukkha as a baseline state, a fundamental wrongness that we usually don't notice until we learn to pay attention, to recognize the subtle discomfort that pervades experience. The warped disk is cosmic dukkha. It's the fundamental unsatisfactoriness in our galaxy's structure, the subtle wrongness that reveals itself only when you measure carefully, when you trace the positions of stars at the galactic edge and realize they're not where they should be if the disk were perfectly flat. The galaxy looks fine from a distance: spiral arms, organized rotation, vigorous star formation. But look closer, measure more carefully, trace the structure with precision instruments, and you find the warp, the distortion, the evidence that something has been pulling on us, that we're not unperturbed, that there's stress built into our architecture, even though most of the galaxy doesn't notice it yet. Trees bent by wind keep their bent shape even when the wind isn't blowing. The deformation becomes structural, built into the wood as the tree grows, a permanent record of prevailing conditions. You can look at a wind-twisted tree and read the history written in its shape, which direction the wind came from, how strong and persistent it was, whether conditions changed over the tree's lifetime. The tree is a living archive of meteorological influence, and the bent trunk tells a story about invisible forces if you know how to read it. Warped galactic disks are the same. They're archives of gravitational influence, records of tidal forces applied over billions of years, stories written in stellar positions about the external forces that shaped them, and we're learning to read those stories, learning to look at the 5,000 light-year deviation at the edge of our disk, and ask what forces could create that, what external influences have been operating long enough to bend a structure as massive as a spiral galaxy's disk. The answer, almost certainly, is multiple influences. The Magellanic Clouds contribute. They're close and massive, and they've been orbiting us for a long time, pulling on our disk with each pass. Internal dynamics might contribute. The galaxy isn't perfectly symmetrical, mass distributions aren't uniform, and asymmetries can drive waves that propagate through the disk and create warping. But Andromeda is there too, in the list of suspects, contributing its distant but persistent gravitational influence, adding its pull to all the other forces shaping our structure, making the warp slightly different than it would be if we were truly isolated. And here's what makes this unsettling rather than merely interesting. The warp is getting worse, or at least it's changing, evolving, responding to forces that are themselves changing as Andromeda falls closer. The tidal force from Andromeda was weaker 1 billion years ago than it is today, and it will be stronger 1 billion years from now. As the distance decreases, as the approach continues, the tidal stress on both galaxies increases. The warps that exist now are just the beginning. The structural deformations we can measure today are evidence of forces that will only intensify, that will only become more disruptive, that will eventually tear both disks apart entirely during the final stages of the merger. We're looking at early-stage damage, the preliminary warping that precedes complete destruction, the subtle bends that will become dramatic tears, the gentle deformations that will become violent disruptions, the structural stress that's currently manageable but which is building towards something catastrophic on timescales of billions of years. Ancient Greek tragedians understood something about how disaster unfolds. It's never sudden, never without warning. Tragedy announces itself through omens and prophecies, through small wrongnesses that accumulate, through subtle deviations from normalcy that careful observers notice and worry about, even when most people don't see the danger yet. Oedipus doesn't suddenly find himself having killed his father and married his mother. The whole play is a slow revelation of what was already true, a gradual uncovering of wrongness that was built into the situation from the beginning. The tragedy wasn't in the final revelation, but in the accumulation of small mistakes and deviations that led there. The warped disk is our galactic omen, the small wrongness that indicates larger problems to come, the structural deviation that reveals forces at work beneath the surface, forces that most of the galaxy doesn't feel yet, but which are definitely present, definitely building, definitely leading toward dramatic consequences, even though the drama won't manifest for billions of years. Beyond the disk, the halo shows its own deformations. The stellar halo, that spherical cloud of old stars surrounding the disk, should be symmetric if the galaxy were isolated and unperturbed. Perfect symmetry is probably too much to expect, given the complexity of galactic formation and evolution, but there should at least be rough symmetry, a generally spherical distribution centered on the galactic center. Instead, when astronomers map the halo carefully using RR Lyrae variable stars and other tracers, they find asymmetries. Lumps and overdensities in some directions, underdensities in others. Streams and substructures that indicate the halo has been stirred and distorted by something. Some of those asymmetries are definitely from mergers. We know the Milky Way has consumed smaller galaxies over its history, and the remains of those galaxies create temporary structure in the halo until tidal forces stretch them into streams that eventually phase mix into smooth distribution. But other asymmetries don't fit the merger explanation easily. They're aligned in directions that suggest external tidal influence. They're distorted in ways consistent with being pulled by a massive object at a specific distance and direction. And when you calculate which massive object at which distance and direction could create the observed asymmetries, Andromeda keeps showing up as a plausible candidate. The dark matter halo shows similar asymmetries, though these are harder to measure because dark matter doesn't emit light and can only be traced through its gravitational effects. Computer simulations of dark matter halos subjected to external tidal fields show that the halos become elongated, stretched in the direction of the perturber, developing tidal tails and asymmetric structure very similar to what we observe in the stellar halo. The invisible architecture is being warped just like the visible structure, bent by the same forces, responding to the same external gravitational influences that are shaping both galaxies. It's like detecting an earthquake by noticing that pictures on walls are slightly tilted. The tilt is subtle. You might not notice unless you're looking carefully, unless you know the pictures used to be perfectly level. But once you see the tilt, once you recognize it as evidence of ground movement, you start noticing other signs. Cracks in plaster, doors that don't close quite right anymore, subtle shifts in how the building settles. Each individual sign could have innocent explanations, but the accumulation of signs points to something systematic, some underlying force that's affecting the whole structure, even though no single piece of evidence is definitive. The warped disk, the asymmetric halo, the streams and substructures, the high-velocity clouds, the stellar streams from disrupted satellites, all of it accumulates into a picture of a galaxy under stress. Not catastrophic stress, not yet. Not stress that threatens stability or causes immediate problems, but stress nonetheless. Persistent, patient stress that's been applied for billions of years and which is building towards something dramatic, even though the dramatic phase won't arrive for billions of years more. There's a Japanese art form called kintsugi, the practice of repairing broken pottery with lacquer mixed with gold, making the cracks and repairs visible rather than hidden, treating the breakage and repair as part of the object's history rather than something to disguise. The philosophy behind kintsugi is that breakage and repair are part of an object's story, that imperfection and damage shouldn't be hidden but acknowledged, that there's beauty in the visible history of stress and healing. The Milky Way's warp is our kintsugi, the visible crack, the structural imperfection that tells a story about forces applied, about stress endured, about deformation that's become permanent. The warp isn't hidden, it's measurable, traceable, built into the structure in ways that reveal history to anyone who knows how to read it. And there's a certain beauty in that, in the idea that our galaxy carries evidence of its gravitational environment written into its architecture, that you can look at the disk structure and read the story of tidal forces and external influence. But unlike kintsugi, where the repair is final and the object enters a stable state, the warp in our galaxy is progressive. It's not healing, it's worsening. The stress isn't being relieved, it's accumulating. The bend isn't reaching equilibrium, it's building toward breaking. We're in the middle of the story, not at the end. The crack is forming, widening, preparing for the moment when it becomes a complete fracture. And that moment, when tidal forces finally exceed the galaxy's ability to maintain structural integrity, when the warping becomes tearing and the bending becomes breaking, is still billions of years away, but is guaranteed by the same forces that created the current warp. Every structure has limits. Every material can only bend so far before it breaks, can only stretch so much before it tears, can only endure so much stress before integrity fails. The Milky Way's disk is currently well within its limits. The warp is survivable, the stress manageable, the deformation something the galaxy can absorb without catastrophic consequences. But the forces creating the warp are increasing. Every million years, Andromeda gets slightly closer. Every billion years, the tidal stress grows measurably stronger. The forces that have created a 5,000 light-year warp over the past few billion years will create much more dramatic deformations over the next few billion years, and eventually, inevitably, these forces will exceed the disk's ability to remain intact, and the structure will not bend but break, will not warp but shatter, will not deform but dissolve. The bent tree shows the wind, The warped disk shows the tidal force. Both are archives of invisible influence, records of persistent stress, evidence that something has been pulling and pushing and shaping structure according to laws that don't care whether the structure wants to be shaped. And we're living inside the warped structure, inhabitants of a galaxy that's already showing strain, that's already bent by forces we're only now learning to recognize, that's being stretched on the cosmic rack, even though most of us never notice the tension, never feel the pull, never recognize that our galactic home is already wounded by the approach of our nearest massive neighbor. The warp is the scar, the evidence, the physical manifestation of gravitational warfare that's been underway for longer than our planet has existed. And it's getting worse, deepening, preparing for the moment when scar becomes rupture and the disk that's currently just bent will be torn apart entirely by tidal forces that are patient but utterly relentless in their accumulation toward catastrophic deformation. Galaxies don't form stars at a steady, predictable rate the way factories produce widgets on an assembly line. If they did, if star formation proceeded smoothly and continuously throughout a galaxy's lifetime, we'd see a very even distribution of stellar ages, old stars from billions of years ago, middle-aged stars, young stars, all in proportions determined by simple math about how quickly stars form and how long they live. The galaxy's stellar population would tell a story of patient, continuous creation, stars being born at a constant rate determined by the available gas supply and the physics of gravitational collapse. But that's not what we see when we look at stellar populations carefully, when we measure the ages of stars in our galaxy using their chemical compositions and their positions on color magnitude diagrams, when we trace the history of star formation written in the demographics of the stellar population. The Milky Way's star formation history is punctuated, not smooth. There are periods of intense star formation, starbursts essentially, though we don't usually call them that because they happened billions of years ago, and we're looking at the archaeological evidence rather than witnessing the events directly. And there are periods of relative quiescence when star formation slowed down, when fewer stars were born, when the galaxy caught its breath between bursts of creative activity. This punctuated history is visible in what astronomers call the age-metallicity relationship. Stars born recently in the last few billion years tend to have higher metallicity, more elements heavier than hydrogen and helium, because they formed from gas that had been enriched by previous generations of stars dying and releasing their processed material back into the interstellar medium. Older stars, born billions of years ago when the galaxy was younger, tend to have a lower metallicity because they formed from more pristine gas that hadn't been through as many cycles of stellar processing. The relationship between age and metallicity should be smooth and continuous if star formation proceeded at a constant rate. Instead, it shows bumps and variations, periods when lots of metal-rich stars formed suddenly, periods when very few stars formed at all. Those bumps are scars, evidence of events. Something disrupted the normal flow of star formation, either triggering bursts by compressing gas clouds or shutting it down by heating gas too hot to collapse. And when you try to figure out what events could create those patterns, what processes could punctuate the star formation history so dramatically, you end up looking at mergers, collisions with other galaxies, gravitational disruptions violent enough to compress gas and trigger starbursts, or to shock heat gas and suppress formation. The demographic data becomes a history book, and what the book tells us is that the Milky Way has not evolved in peaceful isolation, but has been involved in violent interactions that shaped its structure and its stellar population. the most dramatic event in our galaxy's recent past, recent being a relative term when you're talking about billions of years, is something called the Gaia-Enceladus merger. This wasn't discovered until recently, until Gaia provided precise enough data to trace stellar orbits and ages and chemical compositions with sufficient accuracy to recognize that a substantial fraction of our halo stars don't belong to the original Milky Way at all. They're invaders, refugees, the remains of a dwarf galaxy that collided with the Milky Way somewhere between 8 and 10 billion years ago, that was torn apart by tidal forces, and whose stars are now scattered through our halo, following chaotic orbits that reveal their violent origin. The Gaia-Enceladus galaxy, named for the spacecraft that discovered its signature and for a giant in Greek mythology, was probably about 1/4 the mass of the Milky Way at the time of collision. Substantial. Not a minor perturbation, but a major event, a collision violent enough to heat the Milky Way's disk, to thicken it, to disrupt star formation patterns for hundreds of millions of years. The merger happened so long ago that the visible signs have mostly faded. The galaxies have long since merged completely. The orbits have mixed and phase mixed until you can't easily distinguish which stars came from which progenitor. But the chemical signatures remain, the orbital patterns remain, and when you look carefully at stars in our halo, when you measure their metallicities and their orbital properties, you can identify the population that came from Gaia Enceladus and reconstruct the merger that happened 8 billion years ago. And here's what makes this relevant to the current story. Major mergers have consequences that persist long after the merger completes. When a large dwarf galaxy crashes into a spiral galaxy, the spiral doesn't just absorb the dwarf and continue as if nothing happened. The collision disrupts structures. It thickens the disk because stars get scattered onto higher orbits. It changes the distribution of gas because shock waves propagate through the interstellar medium. It alters the gravitational field because mass distributions shift. And those changes affect everything that happens afterward, shaping the galaxy's evolution for billions of years after the collision itself. Did the Gaia-Enceladus merger make us more vulnerable to what's coming with Andromeda? That's a difficult question to answer definitively, because we're comparing two events separated by billions of years, and because isolating causes in complex systems is nearly impossible. But it's plausible that the structural changes from Gaia Enceladus, the thickened disk, the redistributed mass, the altered gravitational field, set up conditions that affect how we'll respond to the Andromeda collision. Trauma has consequences. Damage leaves scars that shape subsequent behavior, and galaxies, like people, carry their history in their structure. Andromeda has its own history of violence, its own evidence of past collisions written in its stellar populations and structural features. One of the most intriguing pieces of evidence is Andromeda's star formation history, which shows a significant burst of star formation about 2 to 4 billion years ago. Something happened during that period that triggered intense star formation across much of Andromeda's disk, creating a generation of stars that's visible now as a distinctive population in age surveys. What could cause such a burst? The leading candidate is a collision with M32, that small elliptical galaxy currently orbiting Andromeda at fairly close distance. M32 is strange for several reasons. It's unusually compact for an elliptical galaxy, with a very high central density, as if it's been stripped of its outer regions, and only the dense core remains. It has a relatively young stellar population for an elliptical, suggesting it had star formation more recently than you'd expect. and its orbit around Andromeda takes it through Andromeda's disk periodically, which is exactly the kind of configuration that would cause strong tidal interactions. The hypothesis, supported by simulations and observations, is that M32 was once a larger galaxy, perhaps a dwarf spiral, that collided with Andromeda, plunged through Andromeda's disk, had most of its outer structure stripped away by tidal forces, and ended up as the compact remnant we see today. The collision would have triggered a massive starburst in Andromeda, as the interloper's gas collided with Andromeda's gas, creating the burst of star formation visible in age surveys. It would also have compressed and shocked M32's own gas, potentially explaining its unusual stellar population. So both galaxies carry evidence of recent violence, recent meaning within the last several billion years, recent on timescales where billion-year-old events are still relevant to current structure. Both have been involved in mergers that disrupted their normal evolution, that triggered starbursts or altered star formation patterns, that left signatures in their stellar populations that careful observers can detect billions of years later. Both are wounded, in a sense, scarred by past collisions, shaped by trauma. There's a creation myth pattern that appears in cultures worldwide. Birth through violence. The world emerges from the body of a slain giant, or from the clash of opposing forces, or from the dismemberment of a primordial being. In Babylonian mythology, the god Marduk defeats the chaos dragon Tiamat and uses her body to create the heavens and earth. In Norse mythology, Odin and his brothers slay the giant Ymir and fashion the world from his corpse. In Hindu mythology, the universe undergoes endless cycles of creation and destruction, each new creation emerging from the dissolution of the previous universe. The pattern is consistent. Creation requires destruction. New things emerge from the death of old things. Birth and violence are intertwined. Star formation triggered by galaxy collisions follows that same pattern. When gas clouds from two galaxies collide, the collision is violent. The gas can't pass through itself the way dark matter can, so the clouds crash together, creating shock waves that propagate through both clouds at supersonic speeds. The shocks compress the gas, raising its density, making it more likely to collapse under its own gravity. And where the compression is strongest, where the shocks converge, new stars ignite, thousands of them, millions of them, forming in a concentrated burst over just a few million years. Birth through violence, creation through collision, new stars emerging from the trauma of galactic warfare. The most extreme examples of collision-induced star formation are ring galaxies. Those spectacular structures where a smaller galaxy punches through the disk of a larger galaxy like a stone dropped in a pond, creating an expanding ring of compressed gas that lights up with star formation as it propagates outward. The ring is a shock wave frozen in time and space, a visible record of the moment of collision, and it's crawling with newborn stars because the compression created perfect conditions for gravitational collapse. These are rare. You need a fairly direct perpendicular collision to create a clean ring, and most collisions are messier than that. But they demonstrate the principle. Collision equals compression equals star formation. Violence creates. So here's the uncomfortable question. Are the current star formation patterns in the Milky Way and Andromeda already being influenced by their mutual approach? Are we seeing the earliest signs of collision-induced star formation billions of years before the actual collision, triggered by the subtle compression of gas clouds responding to the increasing tidal forces and the complex gravitational environment of two massive galaxies falling toward each other? The honest answer is, we don't know. It's incredibly difficult to isolate causes in systems this complex, this massive, with this many variables. Star formation in galaxies is influenced by internal dynamics, the spiral density waves that compress gas as they rotate through the disk, the supernova explosions that either trigger star formation through compression or suppress it through heating, the feedback from massive stars that regulates how efficiently gas converts to stars. It's influenced by the availability of cold molecular gas, which depends on the balance between gas accretion from the intergalactic medium and gas consumption in star formation and gas loss to hot winds. It's influenced by the galaxy's merger history, by dark matter distribution, by magnetic fields, by turbulence in the interstellar medium. Trying to identify a specific external cause, like the gravitational influence of Andromeda, among all these internal processes is like trying to identify which specific factor caused a particular tree to grow slightly taller than its neighbours in a dense forest, where everything affects everything else. You can't run controlled experiments. You can't hold all other variables constant and vary just one. You can only observe, measure, model, simulate, and try to build a consistent picture from fragmentary evidence that's always open to multiple interpretations. But the possibility exists. The gravitational environment is definitely changing as Andromeda approaches. We know that from everything we've discussed in previous chapters. The tidal forces are real and accumulating. The dark matter halos are interpenetrating. The warps and asymmetries demonstrate that external forces are affecting structure, and if external forces can warp the disk, can disrupt satellite galaxies, can accelerate gas clouds into high-velocity trajectories, then it's not unreasonable to think they might also be affecting star formation, might be compressing some gas clouds slightly more than they would be compressed by internal dynamics alone, might be triggering some star formation that wouldn't occur in a galaxy that was truly isolated and unperturbed. The effects would be subtle right now, not dramatic starbursts like we see in ring galaxies or in the final stages of major mergers, just subtle enhancements in star formation rates in specific regions, or subtle suppressions in others, or subtle changes in the spatial distribution of star-forming regions that you'd only notice if you map the galaxy very carefully and compared it to simulations of isolated galaxy evolution. We might be seeing it already, or we might not. The noise in the data might be too large to detect such subtle signals. The internal variability in star formation might swamp any external contribution, but the possibility is there, and it will become certainty eventually as the approach continues and the tidal forces strengthen and the compression becomes strong enough that even the skeptics have to admit something unusual is happening. Freudian psychology, whatever you think of its validity as scientific theory, understood something about how past trauma shapes present behavior. The return of the repressed, experiences that were traumatic get buried in the unconscious, but continue to influence behavior in ways that seem mysterious until you trace them back to their origins. The wounded child becomes the anxious adult, the abandonment becomes the attachment disorder. The early experience shapes the later pattern, even when the connection isn't obvious. Trauma doesn't disappear just because it's not consciously remembered. It persists in structure, in habit, in the ways we respond to situations that resemble the original trauma, even if we don't recognize the resemblance consciously. Galaxies are like that too. The Gaia-Enceladus merger 8 billion years ago is ancient history, but its effects persist in the thickened disk, in the disturbed halo, in the altered distribution of stellar orbits that still carry the signature of that violent collision. Andromeda's collision with what became M32 a few billion years ago is more recent but still history, and yet the burst of star formation from that event is visible in current stellar populations. The stripped structure of M32 is visible now. The gravitational perturbations from that collision might still be propagating through Andromeda's disk as density waves that continue to affect structure and star formation. Past trauma shapes present structure, and present structure will shape future response. When Andromeda and the Milky Way finally merge in 4 billion years, the collision won't be between pristine, untraumatized spiral galaxies. It will be between two galaxies that carry the scars of previous violence, that have already been shaped by past collisions, that have structural features and stellar populations and gas distributions that reflect their entire history of gravitational warfare. The merger will be between wounded galaxies, scarred combatants, fighters who have been through battles before and who carry those battles in their structure. There's a Japanese philosophy about objects gaining character through use and wear. The patina on bronze, the polish on wood, the smooth stone worn by generations of hands. The object's history becomes visible in its surface, and that history is valued rather than hidden, treated as adding depth and beauty rather than diminishing value. An object with history is worth more than an object without, because the history tells stories, reveals how the object has been part of life rather than merely existing apart from it. The disturbed star formation in both galaxies is like that. It's evidence of history, of collision survived, of trauma endured, of structure shaped by events that happened billions of years ago, but which persist in observable ways. The galaxies have character, written in their stellar populations, visible to anyone who knows how to read age distributions and metallicity gradients and spatial patterns of star formation. And that character will affect what happens next, will influence how the collision unfolds, will shape the final result in ways that wouldn't happen if both galaxies were pristine and untraumatized. We're learning to read the history, learning to see the scars, learning to recognize that star formation patterns aren't random but are responses to structure, and structure is shaped by history, and history includes violence. The smooth story of isolated evolution is false. The real story includes collisions, mergers, disruptions, periods of intense star formation triggered by external violence, periods of quiescence when the galaxy recovered and rebuilt. Both galaxies are survivors. Both carry their survival in their structure. Both are approaching the next collision already wounded, already marked by past battles, already shaped in ways that will affect the outcome, even though the outcome is still billions of years away. The disturbance in star formation is evidence, another piece of the puzzle, another sign that the collision has already affected both galaxies, that the gravitational warfare has been underway for longer than we initially realized, that what we thought was pristine structure is actually scar tissue, that what we assumed was normal evolution is actually recovery from trauma. And recognizing that changes how we interpret everything else, changes what we expect from the future collision, changes our understanding of what these galaxies are and what they have been through, and what the merger will mean when it finally arrives, and writes its own chapter in the ongoing story of violence and creation that defines galactic evolution across cosmic time. The word apocalypse has become synonymous with sudden catastrophe in popular usage: asteroid impacts, nuclear war, zombie outbreaks, dramatic, violent endings that arrive quickly and transform everything within days or weeks. The apocalypse in movies and novels and popular imagination is an event, something that happens at a specific moment, that divides history into before and after, that everyone recognizes immediately as the end of the world as they knew it. But that's not what the word originally meant. Apocalypse comes from Greek, apocalypsis, meaning revelation or uncovering, It referred to hidden knowledge being revealed, to secrets being disclosed, to truth that was always there but which becomes visible only when the veil is lifted. The apocalypse wasn't primarily about destruction. It was about revelation, understanding, seeing clearly for the first time things that were always true, but which remained hidden until the moment of disclosure. The collision between Andromeda and the Milky Way is an apocalypse in that original sense. It's a revelation that what we thought was stable isn't, that what we assumed was distant and separate is actually close and entangled. That the future we imagine doesn't exist, because the forces that will transform it are already at work, have been at work for longer than our species has existed, are patient but relentless in their approach toward inevitable conclusion. The veil has been lifted, the hidden truth is revealed, and the truth is that we're living in the opening stages of a transformation that will span billions of years, from beginning to end, but which has already begun in ways we're only now learning to recognize. This is a slow apocalypse, not sudden cataclysm but gradual transformation, not dramatic event but patient process. And that slowness changes everything about how we understand it, how we respond to it, what it means to live with the knowledge that an ending is approaching, but won't arrive for longer than our entire species will likely exist. Let's talk about timescales, because this is where human intuition completely fails us. We evolved to think in terms of days, seasons, years. Our longest historical memories extend a few thousand years. We can trace human civilization back maybe 10,000 years if we're generous, back to the earliest agriculture and the first permanent settlements. Everything before that is prehistory, archaeologically reconstructed, not part of living memory or cultural tradition. 10,000 years is the absolute limit of human historical consciousness. The collision timeline dwarfs that completely. 4 billion years until first contact. That's 4 million millennia. 400,000 times longer than all of recorded human history. If you compressed all of human civilization, from the first farms to the present day, into a single second, the collision would still be more than 4.5 days away. And that's just a first contact. The full merger, from first passage to final settling into Milkomeda, takes another 2 or 3 billion years beyond that. We're talking about timescales so vast that they become almost meaningless, that the human mind can't grasp them in any experiential way, that we can only understand mathematically because we have no intuitive reference for durations that long. But here's what makes it immediate despite the immense duration. The process has already begun. The gravitational influence is already present. The tidal forces are already operating. The dark matter, halos are already interpenetrating. The stellar streams are already forming. The high-velocity clouds are already approaching. The warps are already visible. Everything we've discussed in previous chapters is happening now, tonight, as you listen. The slow apocalypse isn't coming. It's here. We're living through its earliest stages, experiencing the opening movements of a transformation that will take longer than planets typically exist, but which has already started and which will continue with perfect mathematical inevitability until both galaxies are merged into one. Earth won't be here to witness the conclusion. That much is certain. Our planet has maybe 1 billion years left as a habitable world, possibly less. The sun's luminosity increases slowly as it ages, as hydrogen fusion in its core gradually changes the core's composition, and the star's structure adjusts in response. That increasing luminosity will eventually make Earth too hot for liquid water. The oceans will boil, the atmosphere will escape, the planet will become a sterile rock, baked by a sun that's still technically in its main sequence phase, but which has grown bright enough to render the inner solar system uninhabitable. About 5 billion years from now, the Sun will exhaust the hydrogen in its core and begin its transition to red giant phase. The core will contract, heating up, while the outer layers expand dramatically. The Sun will swell to perhaps 100 times its current diameter, possibly larger. Mercury will be consumed. Venus will almost certainly be consumed. Earth's fate is less certain. We might be engulfed, or we might survive in an orbit just beyond the red giant's distended atmosphere, baked to incandescence but not quite swallowed. Either way, Earth as we know it will be long dead, any life long extinct, any trace of human civilization long erased by the Sun's increasing heat and the planet's transformation into a lifeless cinder. The collision's first contact happens around 4 billion years from now. The Sun will be in the early stages of its red giant phase, possibly already swelling, definitely already too luminous for Earth to maintain any surface water. By the time the merger completes, about 10 or 11 billion years from now, the Sun will have been through its entire red giant phase, will have blown off its outer layers in a planetary nebula, will have settled down as a white dwarf, a stellar corpse about the size of Earth, slowly cooling, no longer capable of fusion, no longer capable of supporting planetary systems in any meaningful way. So we won't see it, won't be here, won't witness any of the dramatic stages of the collision because our parent star will die first, and our planet will become uninhabitable long before that, and our species, if it still exists in any recognizable form, will either have fled to other stars or will have gone extinct along with everything else that evolved on this particular rock orbiting this particular star. The collision is our galaxy's future, but not humanity's future, because humanity's timeline is so much shorter, so much more constrained, so completely dependent on a star whose lifespan is measured in billions of years, but which is already past middle age. This creates a strange kind of detachment, doesn't it? We're learning about an ending we'll never witness. We're tracing the opening stages of a process we'll never see complete. We're documenting a transformation that will happen long after every trace of our existence has been erased by time and stellar evolution and entropy's patient work. It's like being told you're living in a house that will eventually burn down, but the fire won't start for thousands of years after you're dead, and even your great-great-great-grandchildren to the 100th generation won't be alive when the flames finally come. Does that knowledge change how you live in the house? Does knowing the eventual fate matter when the timeline is so divorced from any personal stake in the outcome? This is the philosophical challenge of cosmic eschatology, end times that are real and inevitable, but so distant they might as well be hypothetical for any practical purpose. Religious traditions have grappled with this question for millennia. Christian apocalyptic literature, the Book of Revelation being the most famous but hardly the only example, describes an ending that's imminent, that could come at any moment, that believers should prepare for constantly. Therefore keep watch, the Gospels warn, because you do not know on what day your Lord will come. The apocalypse is always approaching, always imminent, always something to prepare for, even though it's been imminent for 2,000 years, and counting, living with that imminence, that constant anticipation of ending, shapes behavior, creates urgency, gives meaning to present actions by framing them against an approaching final judgment. But the Christian apocalypse is sudden. The 7 seals open, yes, but they open in sequence within a relatively compressed time frame. The tribulations arrive quickly once they start. The final battle, the judgment, the new heaven and new earth. All of it unfolds within what seems like years or decades at most. Not millions or billions. It's an event, or a series of events, not a process stretching across timescales longer than species typically survive. Norse mythology's Ragnarök has a longer build-up, 3 years of winter, of social collapse, of increasing chaos before the final battle, but even that is compressed compared to galactic timescales. The ending is approaching, the signs are multiplying, and then the battle comes and the world burns and the surviving gods build anew from the ashes. It's dramatic, it's containable, it unfolds on timescales human minds can grasp. Within a single lifetime or just beyond, close enough to feel urgent, real enough to shape behavior. Hindu cosmology comes closest to the galactic timescale with its concept of yugas, vast ages of cosmic time, each one lasting thousands or millions of years, cycling through creation and dissolution and recreation in patterns so vast they make human history irrelevant. The Kali Yuga, the current age of decline and decay, lasts 432,000 years, according to traditional chronology. That's getting closer to cosmic time scales, at least in conception, though still far shorter than the billions of years we're discussing. But the principle is there. The world is in decline. Decay is built into the structure of time, and we're living through a slow degradation that will eventually lead to dissolution and recreation. The apocalypse isn't sudden. It's the entire Kali Yuga, the whole slow slide toward ending. That's the model that fits galactic collision best. Not sudden catastrophe, but slow decline. Not dramatic event, but patient decay. Not instant transformation, but gradual degradation of structures that were never permanent anyway, that were always temporary organizations of matter, maintained by forces that will eventually fail, that will eventually give way to entropy and gravity and the inexorable mathematics of cosmic evolution. We're living in our galaxy's Kali Yuga, the age of decline, the slow fall toward merger. The structures that define the Milky Way as a spiral galaxy, the disk, the spiral arms, the organized rotation, are degrading, slowly, imperceptibly slowly on human time scales, but degrading nonetheless. The warps are evidence, the tidal forces are evidence, the approach velocity is evidence. Every million years the structures weaken slightly. Every billion years the decay becomes measurable, and eventually, inevitably, the degradation will be complete, the structures will fail, and the Milky Way as we know it will cease to exist, dissolved into the larger structure of Milkomeda. There's a particular kind of dread that comes from slow-moving catastrophes. Climate change is the obvious modern parallel. The temperature increases by fractions of a degree per decade. Sea levels rise by millimeters per year. Ice sheets thin gradually. Ecosystems shift poleward at rates measured in kilometers per year. None of it is fast enough to trigger our evolved threat response systems. None of it produces the immediate fear response that makes us take action urgently. And yet, the accumulation of all those slow changes leads to catastrophic outcomes. Not in a single dramatic event, but in the gradual transformation of Earth's climate into something humanity didn't evolve to survive in. Something that makes our current agricultural systems impossible. Something that forces migration and conflict and suffering spread out over decades or centuries, rather than concentrated into a single moment of obvious crisis. We're terrible at responding to threats like that. Our brains are wired for immediate danger, the snake, the falling rock, the approaching predator. We can mobilize quickly when the threat is obvious and imminent, but gradual threats that operate over decades or centuries, we know intellectually that they're real. We can calculate the trajectories and predict the outcomes, but we can't feel the urgency, can't generate the emotional response that would motivate behavior change. The threat is too slow, too distributed across time, too far removed from immediate experience. The galactic collision is the ultimate slow-moving catastrophe. 4 billion years to first contact, billions more to complete the merger. Timescales so vast that calling it a threat seems wrong because nothing we do or don't do will have any effect on the outcome, and we won't be here anyway, and our sun will be dead and Earth will be uninhabitable. The inevitability is so complete, the timeline so divorced from human relevance, that the appropriate response isn't fear or urgency, but something more like philosophical acceptance, cosmic perspective, the recognition that we're part of processes vastly larger than ourselves, that operate on timescales that make our entire species' existence look like a single breath. But the process has begun. That's the revelation. That's the apocalypse in its original sense, the hidden truth becoming visible. We thought we were living in a stable galaxy that would continue more or less unchanged for billions of years. We thought Andromeda was a distant neighbour that we'd eventually collide with in the far future. We thought the collision was something approaching, something coming, something that hadn't arrived yet. The revelation is that we were wrong about all of it. The galaxy isn't stable. It's already being deformed by external forces. Andromeda isn't distant. Its dark matter halo already reaches us, already surrounds us, already defines part of our gravitational environment. And the collision isn't coming. It's here, unfolding slowly, revealing itself gradually in stellar streams and high-velocity clouds, and warped disks and disturbed star formation patterns. Living in end times, even slow end times, changes how you see everything. Not in dramatic ways, not in ways that affect daily life or immediate decisions, but in perspective, in context, in the recognition that everything you see is temporary, that the structures you assumed were permanent are actually transient, that the galaxy you think of as home is already in the process of transforming into something else, that the ending is written, even though it won't arrive for longer than planets typically exist. There's a kind of peace in that, if you can accept it. The peace that comes from recognizing you can't control or change what's beyond your control, that the universe operates according to laws that don't care about your preferences, that transformation is inevitable and resistance is meaningless. Not fatalism. That would suggest surrender to something that could have been different. Just acceptance, recognition. The understanding that this is how galaxies evolve, how cosmic structures transform over deep time, how the universe builds larger things from smaller things, through patient processes of collision and merger that span longer than conscious beings exist to witness them. The slow apocalypse continues. Every second, the approach velocity carries both galaxies slightly closer. Every year, the gravitational binding strengthens imperceptibly. Every million years, the tidal forces increase measurably. Every billion years, the structures degrade noticeably. It's a countdown that's been running for longer than Earth has existed, that will continue running for longer than our sun will shine, that operates with perfect mathematical consistency, regardless of whether any conscious beings exist to measure it, or understand it, or care about it. We're living through the opening chapter of a very long book, the prologue to an ending that will take billions of years to write fully, the earlier stages of a transformation that dwarfs human history so completely that our entire species' existence will be a brief footnote in the larger story of two galaxies falling together through the darkness, merging over timescales that make civilizations irrelevant, creating something new from the dissolution of both. The revelation is complete, the hidden truth is visible. The slow apocalypse that we thought was future is actually present, unfolding in the darkness around us, patient and inevitable and beautiful in its massive indifference to everything we think matters. And knowing that, understanding that we're living in the opening stages of our galaxy's transformation, that the ending has already begun, even though it won't finish for billions of years, doesn't change anything practical about how we live our lives, but it changes the perspective, changes the context, changes what it means to look up at that faint smudge of light in the autumn sky and know that it's not just approaching us across space, but that it's already here, already touching us, already part of the slow fall that will eventually merge both galaxies into something neither would have become alone. The apocalypse is slow, the revelation is complete, and the ending, when it finally arrives billions of years from now, will be just another chapter in the endless story of matter, following gravity's patient instructions, transforming from one temporary configuration into another, creating beauty through destruction and finding meaning through change in a universe that never promised permanence to begin with. Let's engage in an exercise that's both scientifically rigorous and profoundly melancholic. Let's imagine that humanity somehow survives, not in any realistic sense. We almost certainly won't, for reasons we've already discussed, because Earth will be uninhabitable long before the collision's dramatic phases begin, because our sun will die billions of years before the merger completes. But let's imagine it anyway. Let's pretend that our distant descendants, so changed they might not be recognizable as human, so evolved or modified or transformed that the word descendant stretches almost to breaking, somehow persist through the billions of years between now and first contact, that they maintain some continuity of consciousness, some thread of awareness connecting them to us, some reason to look up at the night sky and remember that their ancestors once called themselves human and lived on a planet called Earth. What would they see? Tonight, if you're lucky enough to be somewhere with dark skies far from city lights, you can see Andromeda with your naked eye. It's faint, barely visible. You need to know exactly where to look, need to let your eyes adjust to darkness for at least 15 or 20 minutes, need to use averted vision, looking slightly to the side of where you think it is, because your peripheral vision is more sensitive to faint light than your central vision. And even then, even under perfect conditions, it's just a smudge, a fuzzy patch. Nothing that would catch your attention if you weren't specifically looking for it. Nothing that would make you stop and stare. Nothing that suggests the massive structure it actually represents. That faint smudge spans about 6 times the apparent diameter of the full moon in the sky. Most people are surprised to learn this because we can't see most of it. The visible part, the part that registers on our retinas, is just the bright central core. But if our eyes could accumulate light the way cameras can, if we could take long exposures and see the full extent of Andromeda's disk, it would dominate the northern sky. It's already large. We just can't see most of it because it's too faint, because our eyes aren't designed to detect very dim light spread across large areas. Fast forward 1 billion years, assuming anyone or anything is there to observe, assuming Earth still exists in some form, even though it will almost certainly be uninhabitable by then, assuming our descendants have somehow found ways to survive as the sun's luminosity increases and the planet bakes. What does Andromeda look like? Larger. Noticeably, measurably larger. Not dramatically. We're still talking about 1 billion years of approach at 110 kilometers per second, which closes maybe 30,000 light years of the 2.5 million light-year gap. It's a small percentage of the total distance, but it's enough that careful observers, if they have records from 1 billion years earlier, which they won't because records don't last billions of years, because civilizations don't last billions of years, because even our most durable monuments crumble to dust on timescales of mere millions of years. But if they could compare, if they somehow had reference points, they'd notice the smudge is slightly less faint, slightly larger, still just a smudge, but a more obvious smudge. 2 billion years from now, Earth is certainly dead by this point, baked sterile by a sun that's increased its luminosity enough that the oceans have boiled away, the atmosphere has mostly escaped, the surface temperature is hot enough to melt lead. But let's maintain the fiction. Let's pretend observers exist somewhere. Maybe they've moved to the outer solar system. Maybe they're living in artificial habitats. Maybe they're not even vaguely human anymore, but they're looking up at the sky from somewhere in what used to be Earth's orbital neighborhood. Andromeda dominates, not just visible but prominent, spanning maybe 15 or 20 moon widths across the sky, bright enough that you'd notice it immediately, impossible to miss even without knowing where to look. The spiral structure is visible to the naked eye now, not in the delicate detail you'd see in photographs, but the arms are there, the dust lanes are there, the overall structure of the galaxy clear and obvious. It's not just another object in the sky anymore. It's a presence, a structure, something that demands attention because it's so much larger than everything else up there, except the moon and planets. 3 billion years from now, the Sun is approaching the end of its main sequence, beginning the early stages of transition to red giant phase. It's significantly brighter than it was during Earth's habitable period, large enough that Mercury has probably been consumed or melted. Venus is a hellscape that makes its current state look temperate by comparison. Our fictional observers, if they still exist, have definitely relocated somewhere farther from the Sun. Maybe they're on moons of Jupiter or Saturn, watching from a safe distance as their ancestral star begins its death throes. And Andromeda. Andromeda is magnificent and terrible, covering perhaps 40 or 50 moon widths, sprawling across a huge chunk of the northern sky, so bright and detailed that individual stars are visible in its spiral arms. Not the faint stars that populate most of the galaxy. Those are still too distant and dim. But the supergiants, the brightest stars in Andromeda's disk, the blue supergiants and red supergiants and hypergiants, stars so intrinsically luminous that even at the remaining distance they shine as distinct points of light, creating new constellations within Andromeda's structure, new patterns that have no connection to the human constellations we know because those will have shifted unrecognizably by this point anyway. The spiral structure is distorted now, visibly warped. The arms that were elegant logarithmic curves in our era are bent and stretched by tidal forces that have grown strong enough to pull the outer regions of both galaxies toward each other. You can see the disruption with the naked eye, can trace where the spiral pattern breaks down at the edges, where stars and gas clouds are being pulled out into tidal streamers, where the organized structure is giving way to chaos as both galaxies begin their final approach. 3.5 billion years. 4 billion. We're approaching first contact now, approaching the first close passage when the visible parts of both galaxies will swing past each other in their spiral dance. The Sun is well into its red giant phase at this point, hugely swollen, possibly having consumed Earth entirely, or at least rendering Earth's orbit a hellish zone inside or barely outside the red giant's distended atmosphere. There are no observers at Earth's position. Can't be, but somewhere in the outer solar system, somewhere safe from the dying sun's expanding envelope, maybe something persists. Maybe some far descendants watch. And oh, what they would see. Andromeda fills the sky, not the entire sky. It's not overhead. It's not surrounding you like the Milky Way's band surrounds you from within. But in the direction of Andromeda, it covers perhaps a third of the visible hemisphere, 60, 70, 80 moon-widths across. So large that you can't take it all in at once, that you have to turn your head to see from one side to the other, that dominates everything in that direction. The spiral structure is severely distorted now, the arms pulled into streamers, the disk warped and tilted. Individual bright stars are scattered across its face like jewels, each one a supergiant that would dwarf our sun, each one pumping out so much light that despite the immense distance they're visible as distinct objects. And the colours. Andromeda isn't monochrome anymore. The starburst regions, those zones where gas clouds from the outer edges of both galaxies have already begun to collide and compress, triggering intense star formation, glow pink and red from ionized hydrogen. The hottest young stars shine blue and blue-white. The cooler giants shine orange and red. The whole galaxy is a tapestry of colours, a painting spread across the sky, more detailed than any nebula we can see in our current era, more spectacular than anything human eyes have witnessed, because nothing in our epoch comes close to the scale and brilliance of a nearby galaxy in the midst of merger. Tidal tails are visible now, those long streamers of stars pulled out by gravitational forces, arcing across the sky like cosmic bridges, connecting Andromeda to the Milky Way's own tidal features. The space between galaxies isn't empty darkness anymore. It's threaded with stellar streams, with bridges of stars, with the visible evidence of gravitational warfare that's been building for billions of years, and which has finally produced structures dramatic enough to see without telescopes, without instruments, just naked eyes looking up at the transformed sky. Australian Aboriginal cultures have concepts of deep time that put Western historical consciousness to shame. The dream time isn't just the past, it's the eternal present, the time when ancestral beings shaped the landscape, when the world was created and defined. Stories about the Dreamtime events are passed down through oral tradition for tens of thousands of years, maintaining continuity of knowledge across timescales that dwarf written history. Rock art sites in Australia date back 60,000 years, potentially longer, preserved and maintained and remembered through generations beyond counting. But even that pales next to the timescales we're discussing. 60,000 years is nothing compared to 4 billion. Even if we somehow maintain a perfect oral tradition, perfect continuity of knowledge, perfect preservation of stories, we couldn't bridge that gap. No oral tradition survives billions of years. No cultural memory persists across those timescales. No monument lasts, no writing endures, no record remains. The descendants watching Andromeda dominate the sky in 4 billion years, if any exist, will have no connection to us except through the most abstract biological continuity, no memory of what we were, no understanding of what Earth was like when it was habitable, no link to the culture and civilization and knowledge that we think of as human. And yet we can imagine what they would see, can calculate the trajectories, can model the stellar populations, can simulate the collision, and produce visualizations showing exactly what the sky would look like at different stages of the approach. We can know their future even though we can't exist to witness it, can describe their sky even though no one will be there to look up at it, and remember that ancient humans once calculated all of this, once knew what was coming, once imagined a future they could never inhabit. Percy Bysshe Shelley wrote a poem called Ozymandias about a broken statue in the desert, a monument to a forgotten king who once commanded empires and who boasted about his mighty works. "Look on my works, ye mighty, and despair," the inscription reads. but the works are gone. Only the ruins remain, half buried in sand, surrounded by empty desert. The poem's narrator reflects on the irony. Nothing beside remains, and the lone and level sands stretch far away. The monument to permanence reveals only impermanence. The boast of eternal greatness highlights only transience. We're building monuments to permanence. The Voyager spacecraft with their golden records, the messages we send into space hoping distant civilizations will find them, the ways we try to preserve our knowledge and culture for hypothetical far future discoverers. But nothing lasts billions of years. Nothing. The Voyager spacecraft will eventually fall into some star or planet. The golden records will be eroded by cosmic radiation. Any messages we send will degrade, will be lost, will become unreadable, even if anyone finds them. The monuments all crumble, the records all fade, and what remains is just the mathematics, the physical laws that governed everything. The same laws that we used to calculate what the sky would look like in 4 billion years, even though we won't be there to verify our calculations. There's something profoundly melancholic about that. Not tragic. Tragedy implies loss of something that could have been saved, implies alternative outcomes that were possible. This is just acceptance of the inevitable. We won't see the beautiful catastrophe we've calculated, won't witness the sky catching fire with star formation, won't trace the tidal streams with our eyes, won't watch Andromeda dominate the northern sky like a cosmic tapestry. All of that will happen, will be real, will be spectacular beyond anything our current sky can show us. But it will happen without witnesses who remember that humans once imagined it, once calculated it, once knew exactly what was coming. Hindu mythology describes yugas spanning hundreds of thousands or millions of years, cycles within cycles, ages of creation and dissolution recurring eternally. At the end of each Mahayuga, the great cycle, the universe dissolves and Brahma sleeps and then creates anew. The cycles are so vast that human lifetimes are meaningless within them, that entire civilizations rise and fall multiple times within a single yuga, that continuity of memory across yugas is impossible. Each cycle starts fresh, with no knowledge of previous cycles, with no memory of what came before except perhaps in the most abstract mythological sense. We're living in our own version of that. Not a cycle, the collision happens once, at least between these two particular galaxies, but the same vast timescales that make continuity impossible, that make memory meaningless, that divorce cause from consequence so completely that the beings who experience the consequence can't possibly know about or remember or relate to the beings who predicted it. We're the Brahma of this story, calculating the shape of the next creation, but we won't be around to see it manifest, won't persist to witness whether our calculations were accurate, won't have any connection to whatever exists when the beautiful sky we've imagined finally appears. And still we calculate it, still we imagine it, still we use physics and mathematics to project forward billions of years, to describe skies that no human eye will ever see, to trace the evolution of stellar populations and tidal structures and star formation patterns across timescales that dwarf our species' entire existence. Why? What's the point of imagining futures we can't inhabit, of describing events we'll never witness, of calculating the details of a spectacular sky that will unfold in the complete absence of anyone who remembers that we once knew it was coming? Perhaps because it's what consciousness does. We predict, we imagine, we project forward even when the projections extend beyond our own existence, beyond our species' existence, beyond any continuity of knowledge or memory or culture. We calculate futures we can't inhabit, because the calculation itself is valuable, because understanding is its own reward, because knowing what will happen, even if we won't be there to see it, is somehow fundamentally important to what it means to be conscious beings embedded in a universe governed by comprehensible physical laws. The sky of our descendants will be magnificent, more spectacular than any sky humans have ever witnessed, more dramatic than any aurora, more colourful than any sunset, more structured than any zodiacal light or Gegenschein, or any other subtle phenomenon we currently marvel at. The sky will be on fire with creation and destruction happening simultaneously, with tidal forces tearing old structures apart, while compression ignites new star formation, with two massive galaxies interpenetrating in a dance that spans millions of years, but which, from a human-scale lifetime, would appear almost static, a spectacular sculpture frozen in the sky, unchanging within any individual lifetime, but evolving dramatically across generations. But there will be no descendants to see it. That's the revelation we have to accept. The calculation is real. The prediction is accurate. The sky will be magnificent, and it will unfold in a universe devoid of anyone who remembers that humans once lived on a planet called Earth, once looked up at a faint smudge called Andromeda, once calculated exactly how that smudge would grow and transform and dominate the sky across billions of years of patient approach. We're writing a story about a sky we'll never see, imagining a future we can't inhabit, calculating beauty that will manifest in our absence. And there's something both sorrowful and strangely satisfying about that, about the recognition that we can know what's coming even though we won't be there, that we can describe the spectacular finale even though we'll only experience the quiet prologue, that we're living in the opening chapter of a story that won't reach its climax for longer than our species will exist, but which we can nonetheless trace from beginning to end through nothing but physics and mathematics, and the patient application of physical laws across unimaginable timescales. The sky of our descendants will be magnificent. We've calculated it. We've imagined it. We've described it in detail, and it will unfold exactly as we've predicted, in perfect accordance with physical law, in complete indifference to whether anyone exists to witness it, or to remember that ancient humans once knew exactly what was coming, and once looked up at a faint smudge in the autumn sky, and recognized it not as something small and distant and irrelevant, but as their galaxy's future, their inevitable partner in transformation, the source of the beautiful catastrophe that would reshape everything across timescales so vast. They make human ambitions and human monuments and human dreams of permanence look like brief flickers in an endless night. The sky will burn, will glow, will transform into something spectacular beyond current imagining. And it will do all of that without witnesses, without memory, without anyone to look up and recognize that the spectacular sky was predicted, was calculated, was known billions of years before it manifested. Just physics following its own rules, matter following gravity's patient instructions, the universe being itself with perfect consistency across timescales that make consciousness irrelevant and continuity impossible. Our descendants won't see it because our descendants won't exist. The sky we've calculated is real but unwitnessed. The beauty we've imagined is accurate but unseen. And somehow that makes it more profound rather than less, makes the calculation more valuable rather than meaningless, makes the act of imagining unwitnessable futures a strange kind of gift. We leave to a universe that doesn't need the gift and won't remember we gave it. So, let's return to where we started, to tonight, to right now, to this moment before sleep when you're settling into rest, and the universe continues its patient work in the darkness around us. The collision between Andromeda and the Milky Way isn't coming, it's here. That's been the revelation, the apocalypse in its original sense, the uncovering of hidden truth. The war you can't see has been raging for millions of years, will continue for billions more, and surrounds us with evidence once you learn to recognize the signs. Gravitational whispers accumulating into inevitable consequence, dark matter, halos already interpenetrating in the space between galaxies, stellar streams marking where small satellites were torn apart, high-velocity clouds moving wrong too fast, harbingers of chaos written in neutral hydrogen, the warped disk, the twisted halo, the disturbed star formation patterns, all of it evidence of stress, of forces at work, of transformation already underway. Tonight, right now, as you drift towards sleep, Andromeda is pulling on every atom in your body. 1 nanometer per second squared. Almost nothing, but that almost nothing has been accumulating for longer than complex life has existed on Earth, building velocity and momentum across timescales so vast that the words past and future start to lose their meaning. The pull is patient, the fall is slow. Both are real, both are shaping trajectories that will eventually merge two massive galaxies into something neither would have become alone. Both galaxies carry scars from previous violence. Their star formation patterns reveal histories of collision and merger, evidence that they're not pristine structures meeting for the first time, but are already wounded, already marked by gravitational warfare, already shaped by trauma billions of years old. The Milky Way remembers Gaia Enceladus, that massive merger 8 billion years ago that thickened our disk and scattered stars through our halo. Andromeda remembers its own collisions, its own consumption of smaller neighbours, violence written in its stellar populations for anyone who knows how to read the demographic data. And the timescales. The timescales are so vast they become almost meaningless in human terms. 4 billion years to first contact. Billions more to complete the merger. We won't witness any of the dramatic phases, because Earth will be dead, and the Sun will have died, and our species will be long extinct by the time the visible fireworks begin. The sky we've calculated, that magnificent, terrible sky with Andromeda dominating like a cosmic tapestry, starburst regions glowing pink and blue, tidal tails threading through the darkness. That sky will unfold in our complete absence, witnessed by no one who remembers that humans once predicted it, once knew exactly what was coming. There's a particular kind of acceptance that comes from understanding you're living through the prologue of a story that won't reach its conclusion for longer than your species will exist. Not despair. Despair implies hope for a different outcome, just recognition. The universe operates according to laws that don't care about our preferences, that will transform galaxies whether or not anyone is watching, that create beauty and destruction on time scales, that make consciousness itself seem like a brief flicker against eternal darkness. The slow fall continues. Every second, both galaxies move slightly closer. Every million years, the gravitational binding strengthens measurably. Every billion years, the structures degrade noticeably. It's a countdown that's been running since before Earth existed, that will continue running for longer than our sun will shine, that operates with perfect mathematical consistency, regardless of whether any conscious beings exist to measure it or understand it or care about it. And here we are, conscious beings who happen to exist during a tiny sliver of that countdown, during the opening chapter, when the effects are still subtle enough that most of the universe doesn't notice, but obvious enough that careful observers with good instruments can detect them. the privilege of living during the era when the collision transitions from completely hidden to barely visible, when the revelation occurs, when the apocalypse, in its original meaning, unfolds and shows us that what we thought was stable isn't, that what we assumed was distant is already here, that the future we imagined as safely remote is actually present and unfolding in the darkness around us. Look up at Andromeda tonight, if you can find it. That faint smudge in the autumn sky, it looks innocent, distant, separate, just another object in the cosmic catalogue, no more threatening than any other galaxy scattered across the observable universe. But now, you know what it really is. Not just a neighbour, but a partner in transformation. Not just approaching, but already here, already touching us through its dark matter halo, already pulling on us with forces too subtle to feel, but too persistent to ignore, already writing the opening chapters of a merger that will take longer than planets typically exist, but which has already begun in ways we're only now learning to recognize. The collision isn't coming, the collision is here, the slow fall that will eventually bring both galaxies together into Milkomeda has been underway for longer than our species has existed, and will continue for longer than our sun will burn. And we're living through it, passengers on a galactic trajectory we can't change, witnesses to the opening act of a drama that will unfold across billions of years, conscious for just long enough to recognize the pattern, to understand the forces at work, to calculate the ending even though we'll never see it. Sleep well in the knowledge that some transformations are so vast they make human history irrelevant, so patient they operate on timescales that dwarf species' lifetimes, so inevitable they render worry meaningless. The approach continues. The fall proceeds. And tonight, as you drift into darkness, the same forces that will eventually merge two galaxies are already at work, already shaping trajectories, already writing the slow apocalypse that we're privileged to witness in its earliest, quietest, most subtle stages. This is the Sleepy Astronomer, wishing you peaceful dreams in a universe where the collision has already begun, where the war you can't see surrounds you, where two massive galaxies fall toward each other through the darkness with perfect patience and inevitable grace, where the ending is already written even though it won't arrive for billions of years, where everything you think is stable is actually transforming, slowly, invisibly, beautifully across timescales that make our brief consciousness seem like a single breath in an endless conversation between massive objects following gravity's patient instructions toward their inevitable merger in the distant but certain future that's already casting its shadow backward into the present we inhabit.